Good morning, America. Good afternoon, Europe. Good evening, Asia and Pacific. This is the 7th CIRPe Global Web Conference hosted by the International Academy of Production Engineering. It is our great honor to welcome you to this opening session of the conference. In the forthcoming 3 days, we are going to broadcast this conference live from our studios in Berlin. The opening session will have 4 parts. The first part is the CIRPe conference and its mission in the world of CIRP. The second part, what's new in this year's CIRPe conference, innovations and key facts of this year. The third part is about how to participate, how to disseminate and more technical info. And the fourth part is about the technical program of this conference. Let me start with the conference to explain the fundamentals. The CIRPe Global Web Conference is hosted by the International Academy for Production Engineering. Each year it is chaired by volunteer research affiliates and it is sponsored by 2 different CIRP fellows. The contents is peer-reviewed by senior CIRP members and other experts beyond. The papers are published in Procedia CIRP at Elsevier. The conferencing format is purely digital, which means that there is no physical conference, but only online streams. You are now attending the 7th CIRPe Global Web Conference, which stands in a row after 6 CIRPe Global Web Conferences established from 2013 on. From its first year on, the CIRPe Global Web Conference has been a pioneer in digital conferencing. However, just to have an online conference in its portfolio is not the only purpose of CIRPe in the world of CIRP. In order to understand this, it is important to know that the mission of the CIRPe Global Web Conference is closely related to the purpose of the CIRP Research Affiliate Program by which it is organized. The CIRP Research Affiliate Program shall give young researchers in production engineering the opportunity to get involved with the International Academy for Production Engineering. Being honored as a research affiliate, these young researchers are encouraged to contribute to the mission of CIRP and to establish their bonds within the network of CIRP. Since the research affiliates have their interests spread across all scientific technical committees of CIRP, it is at the heart of the CIRPe Global Web Conference to reflect this large cross-STC variety of topics. However, in the view of this year's conference chance, one should not become distracted and look at the variety of topics as it was just a loose, unsorted compilation of everybody's research interest. Instead, we are strongly convinced that the CIRPe Global Web Conference can only add something new to the world of CIRP if there is a common theme which sets each individual paper in a context. The third point is about impact maximization. When we volunteered to chair and organize the conference, we thought that not only scientific quality is the key to maximum impact, but that it is also about the way these results are communicated. We hence strived for new conferencing formats, which you will see later. The fourth point goes to the address of the researchers who are in their very early stages. The CIRPe Global Web Conference may help these aspiring novices to train their scientific skills under the guidance and review of experienced and seasoned CIRP members. During the review process of this year's CIRPe, we were really delighted in how much detail the vast majority of the reviews helped the authors to improve and learn, and also to see how intense the authors made their efforts to reply to these efforts. We were very happy to see that the authors appreciated this feedback and worked with considerable effort to meet these expectations. The fifth point is about accessibility of the conference and its information. In difference to all physical conferences, the purely digital conferencing format makes it very cheap and very time efficient to publish, and the digital nature of the online contents makes it pretty straightforward to do marketing in your own interest. We hope you do so as much as possible. CIRPe Global Web Conference and the CIRPe Research Affiliates program are all about interaction within the CIRP network, even if it might seem not very present because it's not physical at first sight. The first perspective I'd like to share is the interaction the CIRP members have with the conference. For example, each CIRPe Global Web Conference has 2 CIRP fellows as sponsors, which interact with us as chairs to ensure that the conference is run to CIRP quality standards. We have encountered that these sponsors do discuss their point of view and our innovations with a number of other CIRP fellows, which themselves become interested and discuss. Furthermore, an appreciate number of CIRP members volunteer to do paper reviews. This means that they get to know the author's research and feedback interaction evolves, even if you are at the very early stages of your career. It is this particular interaction with very low barriers which lets seasoned CIRP members encourage their young researchers to publish at the CIRPe Global Web Conference. The second perspective I'd like to take is from the CIRP research affiliates and authors beyond. The CIRPe Global Web Conferences is a valuable context for research affiliates and their teams to interact with the CIRP network. First, the CIRPe Global Web Conference is an effective and efficient way to publish in the CIRP world. It is effective in that sense that CIRP members do take notice. We as chairs did our best to assign suitable reviewers, and many reviewers gave feedback that they enjoyed reading your papers. It is efficient in the sense that it does not consume too much money and travel time to participate and attend the conference. Second, we observe that CIRPe Global Web Conference is a place for very explorative topics. You will find a number of papers in the program which are real surprises in that they contain really fresh ideas, and that is what we were seeking for when we volunteered to chair the conference. Third, CIRPe Global Web Conference helps to pin down the fruitful discussions the research affiliates have among each other in their meetings. We have introduced the highlighted papers in order to give these discussions a target and a frame. We called for groups of research affiliates who wanted to condense their workshops and collaborative efforts in papers that are visible. I'm very delighted that this innovation was successful and that we can hear 2 of these papers just right after this opening sessions that we are in right now. The fifth point I wanted to mention in terms of interaction between research affiliates and the CIRP network in the context of CIRPe is the training aspect. We have observed that especially those of you who are new to the world of CIRP make extensive use of the opportunity to learn about CIRP, the benefits and the standards therein. Also, the experienced colleagues of you have made considerable contribution to give guidance to younger colleagues. Let me do one final statement about the mission of the CIRPe Global Web Conference in that sense. Due to the fact that the CIRPe Global Web Conference is not limited to a particular topic, it is a very good idea to add new perspectives to the CIRP network. With this, we mean new scientific perspectives and new innovative conferencing formats in order to foster the support of the CIRPe Global Web Conference as a valuable contribution to the world of CIRP. May this year's CIRPe Global Web Conference be a fruitful outcome of everybody's effort. It was said before that the nature of CIRPe is about cross-domain research. Moreover, the importance of a common theme was stressed in what I said earlier. These 2 thoughts and the many discussions that we had as research affiliates at the workshops, general assembly meetings and so on helped us to develop this year's conference theme. The theme revolves around the question how and why production value stream patterns will shift when data, models and technology is inferred. This goes back and was sparked when Marcel Fay from the WZL in Aachen, he proposed a research affiliate workshop with the question, how would Google build a machine tool? This question may sound very straightforward to answer, but the more we discussed, the more the different approaches were elaborated. In all the discussions since, it was clear that only cross-domain research would lead to such answers, and we are happy that the program of this year's CIRPe Global Web Conference reflects these thoughts at their core. The group of people who attended this workshop are now present in a manifold of papers. Moreover, the conference scheme that we chose this year is pretty much inspired by this workshop. In the following Research Affiliates meeting, the workshop discussions were again and again dragged towards a topic that were beyond or in between established boundaries of scientific technical committees of CIRPe. And this was the reason to choose this year's conference towards shifted production value stream patterns through inference of data, models and technology. Before I will introduce the program in more detail, let me outline the innovations we will introduce in this year. First, we introduced what we call highlighted papers, and I have spoken about that before. These papers shall highlight collaborations among research affiliates and shall give perspectives of these groups. I'm happy that we can announce 2 of such papers this year and that a considerable amount of research affiliates have grouped around these papers to prepare them, to compile them, and to prepare the presentations that we will see right after this opening session. Second, we have received a number of 72 abstracts this year, of which 52 abstracts have been reviewed, and on the basis of 113 reviews that we received back, 47 research papers have been accepted to be in the final schedule. Third is the introduction of the industry panel discussion, which evaluates all 47 research papers from industry perspectives. The fourth thing is we are live on YouTube, which is also a novel format that we wanted to try out this year for better broadcast and better accessibility. Such a conference is an outcome of many people's contribution, support and effort. I'd like to highlight the main group of people who we have found was very supportive for us in the way on the organization of this conference. First, let me appreciate the support of the 2 CIRPe fellows who have approved this activity and who have given valuable feedback to our way we organize the conference. This goes to Professor Jürgen Fleischer from KIT Karlsruhe, who I've just spoken to on the phone 5 minutes ago, and to Professor Samikara, who is affiliated to the University of New South Wales in Sydney, Australia. Second, the many volunteers who participated in the International Scientific Committee of this conference, who did numerous reviews and who gave us valuable feedbacks in all the bits and pieces and details of the conference organization. These are the people who make it worth to submit your paper to the conference because they have provided in-depth feedback to the numerous count of papers. Third, while we organized the schedule of the conference, we came to know Oliver Schwabe. He is with Rolls-Royce and he is keen with innovation management. We are delighted that he proposed to have an industry session and that he has put a lot of effort in organizing it. Thank you, Oliver. I personally like to address a thank you to my co-chair, Nicole Krenkel, from Kaiserslautern University. Together, we volunteered at the General Assembly in Tokyo to chair this conference. Thank you, Nicole, for taking this adventure with us. It was a great team experience and it was very inspirational for us so far. Originally, we planned to have Nicole Krenkel with us live in our broadcasting studio in Berlin. Unfortunately, we had to change this plan since she fell ill in the last few days and she had to see urgent medical treatments. For this reason, she was not able to travel and will only be able to follow this event from her recovery at home. Nicole, the whole team who sits just right here behind me, they send their deep feelings for you, for your fast recovery. Get well back soon. I would also like to express my appreciation to my team here in Berlin, and I'm looking to the team over there, which you can't see. They are right behind the camera here. Their strong support means a lot for the experience that we can now deliver to you. At the forefront, there are Pina Bilge and Arne Glodde, who have spent considerable time and thoughts to make this happen. Also, please let me mention Alexandra Weber, Cesar Solmas, Uli Ringeisen, Sabine Lange and Raju Odai for their support. Thanks to the team. I will now come to the next part of this kind of opening session, and I'd like to introduce Arne Glodde to you. He is a postdoc at my chair, and he is responsible for all the technical stuff, and he is going to give you some more information about your participation and interaction. Arne, welcome.
Thank you, Franz, for giving me a short chance to have a short talk here. All live streams will be broadcasted on this channel first, so this is here welcoming your start in here. At next, we will have the highlighted papers here on this channel, and afterwards we will start a second YouTube channel, which you also find on this channel, to have the paper session there in parallel. This stream will start at around 13 o'clock. So then, thank you, and we're hoping to see you soon.
Thank you, Arne, for joining us. To the authors, you will be contacted by Arne and the other camera control room to prepare the question and answer session. The informations for you as a viewer, in order to make the most out of this purely digital format, it's very important for the conference and for the other authors of the papers that you participate actively. And this means that we want your feedback, the authors want your feedback, and we ask you therefore to post your comments during the video presentations below the live stream and the YouTube comments. During the presentations, we will collect your question and then discuss them live in a question and answer sessions in a video call with the authors. If any technical flaws occur, please be patient with us. It is our first online conference and we will do our best to have it as smooth as possible. Some information for the authors. We'd kindly ask the authors to be online and to react to other viewers' comments in the live stream when their paper presentation runs. And also, please, dear authors, be ready for a viewer-friendly question and answer session. We will call you on Skype while your presentation video runs. The next part of this opening session is about the dissemination of the contents in your own interest. And for this purpose, I am delighted to introduce Pina Bilge to you, who is occupied, besides the moderation, also with the dissemination. Pina, thanks for having you here.
Thank you, Franz. Welcome also from my side to the CIRPe Global Web Conference. For the dissemination of the conference, please feel free to post your contribution and as well as the conference on any social media channel. As usual for CIRPe conferences, the papers are going to be published through the CIRPe procedure on Elsevier sites. The videos which are presented within the next 3 days are going to be also online after the conference on YouTube. And please feel free also to use our hashtag if you want to put a post on any social media channel and use the hashtag CIRPe. Thank you.
Thank you, Pina, for giving us this information. We are really keen to see how that develops in the social media, so feel free to comment and to give us feedback about how the conference goes, about the content, how we're doing, and so on. The next part of the opening session is about the technical program that we're going to broadcast live to you in the next coming 3 days. Let me start with what I have announced earlier, the highlighted papers. After this session, we are going to have 2 highlighted papers. These papers are outcomes of collaborative work of research affiliates, and you can count it from the list of authors that have done that. The first paper that we're going to show is entitled Shifting Value Stream Patterns Along the Product Life Cycles with Digital Twins. It is presented by Benjamin Schleich, and the co-authors will be Marc Dittrich, Till Klausmeier, Roy Damgrave, John R. Koyonshu, Benjamin Heffner, Joost de Lange, Dennis Blakotnik, Wieben Scheidel, and Thorsten Wüst. The second paper, also coordinated and written by a group of research affiliates, is entitled Highlights in Customer-Driven Operations Management Research. This one is presented by Khaled Medini from France, and it is co-authored by Anne-Louise Andersen, Thorsten Wüst, Björn Christensen, Stefan Wiesner, David Romero, Ang Liu, and Fei Tao. Thank you for doing the efforts. Thank you for condensing all the contents that has been created throughout the past research affiliate meetings and other discussions into these highlighted papers. The second highlight in the program that I want to elaborate a bit more with you is the industry panel discussion. This one is going to take place at the very end of the conference on Friday at 12 o'clock, and is going to take 1 hour. This is led by Oliver Schwabe, and he is keen about innovation management, and he has established a method that evaluates technologies for their industry readiness, and he has taken the effort to acquire a team of industry specialists and make them go through this method. We will now try to get him live here into that session and see whether he can tell us something more about his session. Oliver, we have you on the screen right now. Hello, can you hear us?
Okay. Can you hear me?
Yes, Oliver, hello. Hello from Berlin. It's very good to have you here. Can
you hear me without delay?
Yes, very good. Thanks for joining us in this session. We're now right in the opening session, and we are happy to learn more about the industry session that you are going to host on Friday, 12 o'clock. Oliver, can you hear me?
Okay, so the video seems to be slightly delayed, so I don't know how quickly this is going to come across. I'll try it.
Yeah, okay. Yeah. Can you explain something more about the industry panel?
So
yes.
Welcome everyone. Thank you again to Franz and the team for, I think, a wonderful event. Okay. Yeah, okay. So what we did was, along with some colleagues, we asked ourselves the question of the conference contribution is okay, this is scrambling slightly. In the end, okay, so what we're going to do, we evaluated from an industry perspective every single paper that was submitted, and we assessed readiness for implementation in the company. And I've sent an email to everyone, and on Friday we will discuss what it takes to make a paper ready for implementation in the company. General, this is about what the attention that Rolls-Royce, and it's also about supporting all of the authors, perhaps write papers which are a bit easier for industry to appreciate, to pick up and discuss with you. So join us on Friday. Every single paper is evaluated. If you have interest in individual scores or assessments, respond to my email or reach out.
Thank you. Thank you, Oliver, for joining this thing. We are appreciating really very much that you have put together the method. We appreciate that you have put together the panel from the experts from Rolls-Royce. We have other experts also from academia and all other companies. And we are really looking forward to that session on Friday. Thank you very much and goodbye. The next thing that I wanted to show you on this opening session is to go through the program and the structure of that conference. Due to the number of time zones from which we received contributions, which were as spread apart as in the US, from Europe and from Asia and Australia, we decided to squeeze the conference schedule within a very short time frame within each day. This urged us towards using 2 parallel streams in order to get all the papers that you wanted to have in the schedule on the live stream. So we will have 2 live streams. Live stream 1, which is the stream that you're watching right now, is on the left. Live stream 2, which you will find the link below in the description and on our YouTube channel. This is going to this is the way we're going to broadcast the conference. We are now in the opening session, and afterwards you will see 1 hour of highlighted papers. 30 minutes per paper will be there. Afterwards, the paper sessions will start. Each paper is assigned with 20 minutes. And on this live stream, we're going to start with a session about shop floor operations and maintenance. And the second live stream will be about automation planning and configuration. The second live stream will be moderated by Pinar Bilge over there in the studio right next door. Tomorrow we are going to start the stream at 10 to 12 in German time. After a short opening session, the live stream 1 will be about form-based processes and metrology. The second part will be about cutting, grinding and spindles. The third part will be about value streams and lifecycle engineering topics. On the second live stream, we're going to have a paper session first about robotics, automation and assembly. And the second part is about additive technologies, coating technologies, hybrid manufacturing, and incremental manufacturing. The third day will have papers on both streams about value streams and lifecycle engineering. And we're going to close the conference on live stream 1 by using by having the industry panel discussion on this stream that you're watching right now. You will find on our YouTube channel, you will find sessions, live streams scheduled for each of the days, for each of the live streams. So feel free to navigate around to see at which live stream we are going to broadcast live to you. Before we come to the end of this opening session of the 7th CIRPe Global Web Conference, I'd like to have an announcement right here about what is going to happen next year. Plans have started to do so, and I'm really happy to welcome Karel Kellens in our studio. He's a professor at KU Leuven, and he has decided to have a theme about flexible mass customization in next year's CIRPe Global Web Conference. Karel, come in. Hi.
Hi.
Good to have you here.
Hello. Thank you, Frans. I'm really happy to have the opportunity to come here and to already have a short announcement about the edition next year and to see in real life in this pop-up studio how well the conference is prepared and organized. So hopefully your team is free next year in October as well. Good. Maybe I can just already move to the next slide. So next year the conference, today we are in Berlin, next year we will be in Leuven to broadcast all the nice presentations of the CIRPe conference. We decided to have a team, one global team next like this year, about flexible mass customization, and the conference will take place in the same week from the 14th to the 16th of October 2020. So I will not organize the conference myself, but I have some co-chairs around in Leuven, so Professor Ferraris and Professor De Meester. They will assist me, or I will assist them, in organizing the conference. And of course also we will have some scientific sponsors by Professor Kroet from KU Leuven in Belgium and Professor Teti from the University of Naples in Italy. As a tradition, and which is a nice thing the last few years, of course we will welcome all papers related to the central theme of flexible mass customization, coming from all the different SCCs, having a broad perspective on the theme. So hopefully we will get some papers from every SCC within CIRP, which will of course have a nice representation from all sides. And then, to round up, I would like to end with some dates. And the most important thing, of course, is that from the 15th of February next year, we will start spamming you with a lot of information about the conference, asking for contributions, looking forward to receive abstracts, full papers, and so on. But all these days, of course, will be communicated along at the right moment. So that for next year, and then I would like to wish all of you a nice conference the coming 3 days. I'm really convinced it will be a success and a nice time around. So Frans,
Thank you for
good
being
luck,
here.
and
It's really nice to have you here in Berlin to join us here and attend the conference live here from Berlin, from the studio. Thank you very much.
thank you.
Thank you. Okay, this brings me to the end of the opening session. We are really happy to see you here live on that web stream for the 7th CIRPe Global Web Conference. Feel free to comment in the live stream. Do post, use CIRPe as a hashtag there. We are really looking forward to the interaction and we are really keen to see how that digital conferencing format can lead us into the future of climate-friendly conferencing. We are now approaching the highlighted paper session that I want to start right now. So we are going to have 2 highlighted papers in there, and the first of these highlighted papers, maybe we can see the first page. Thank you. The first highlighted paper that we are going to see right now is entitled Shifting Value Stream Patterns Along the Product Lifecycle with Digital Twins. It is written by Benjamin Schleich, Marc-André Dietrich, Till Klausmeier, Roy Damgrave, John Erkoyonschu, Benjamin Heffner, Joost de Lange, Dennis Plakotnik, Wieben Scheidel and Thorsten Wüst. We are really looking forward to this paper, to the collaboration which is multinational and which has had a really strong dynamic process in writing the papers. We are really looking forward to that. Let's play.
My great pleasure to welcome you also on behalf of all my co-authors, Mark, Till, Roy, John, Benjamin, Jos, Dennis, Wieben, and Thorsten, to the presentation of our paper entitled Shifting Value Stream Patterns Along the Product Lifecycle with Digital Twins. The outline of this presentation is as follows. Firstly, I will give a brief introduction and motivation to the topic. I'll then review a definition of the digital twin that we used throughout the paper, and I will say some words about some core enabling technologies of the digital twin. In the main part of the presentation and also of the paper, we will then sketch some use cases of digital twins over the product lifecycle and explain some new value stream patterns across the product lifecycle that we can achieve with digital twins. Finally, we'll also, of course, give a conclusion and an outlook. So what is the motivation of our paper? Actually, as we all know, during the last 25 years, information and communication technologies have shaped industrial production and drastically also shifted production value stream patterns. For example, computers and simulation systems in product development and process planning have become state-of-the-art. So this is actually displayed at this slide. We see that today virtual product development is actually done and performed in completely virtual 2- or 3-dimensional environments. And we use a lot of different modeling and simulation technologies, like, for example, computer-aided design or different computer-aided engineering methods like multi-body simulations or computational fluid dynamics, and also different tools for computer-aided manufacturing. However, what we also see today is that there is an increased data exchange between these different virtual models and also between the virtual and the physical world. This is also driven by increasing possibilities in sensor technologies. And this actually leads or thrives us to the paradigm of a digital twin. So we see that we have some technological fundamentals to achieve digital twins, but the actual benefits of such digital twins remain somehow unclear and vague, and only few actual use cases can be found. And this observation is also supported by an analysis on emerging technologies by Gartner. And according to their findings, digital twins are currently in a stage of inflated expectations. And because of this, further research and development activities are necessary to establish a solid technological framework for digital twins. And this is actually the motivation of our paper. However, we first of all have to somehow define what we actually mean by the term digital twin. And as you all know, there are different definitions of this digital twin available. For example, one is established by the NASA, and they define a digital twin as an integrated multiphysics, multiscale probabilistic simulation of an as-built vehicle or system. And this is actually focusing on the simulation perspective of a digital twin. There is also a definition by Greaves, for example, and he defines a digital twin as a set of virtual information constructs that fully describes the potential or actual physical manufactured product from the microatomic level to the macro geometrical level. And we see from this definition that he is more focusing on the PLM, the product lifecycle management perspective. However, with the aim of bridging the gap between these partially diverging understandings, there is also a definition by Stark and Damarau, also on behalf of the International Academy for Production Engineering, and they define a digital twin as a digital representation of an active, unique product, which may be a real device, an object, a machine, a service, or an intangible asset, or a unique product service system, for example, a system consisting of a product and a related service that comprises its selected characteristics, properties, conditions, and behaviors by means of models, information, and data within a single or even across multiple lifecycle phases. And this is quite a broad definition, but we think it is quite useful, and this is why we also used it throughout the paper. Beside this, for us, it was also quite important to stress out that the digital twin itself is also relying on some enabling technologies, and it is closely connected to these several emerging technologies, like, for example, sensor technology or cyber-physical systems, sophisticated simulation models, and also approaches for machine learning and artificial intelligence. And this is just, I will not go into detail on these different technologies, but for us it's important to know and to stress out that the digital twin is always relying also on some technologies for data collection, for like sensors, for data transfer, like for example also the Internet of Things, and of course also for data processing, like cyber-physical systems or sophisticated simulation models and machine learning approaches. But what are actually the main use cases of digital twins over the product lifecycle? This is the first question that we tried to answer in our joint paper, and we thought it's a good idea to structure the product lifecycle following the three-phase product lifecycle model, which is quite commonly used in the engineering domain, and it basically splits the overall lifecycle in three distinct phases, namely the beginning of life, the middle of life, and the end of life. And the focal topic of this paper, digital twins, so we decided to split the beginning of life phase into subcategories, the design and the manufacturing, because there are distinct differences in these two phases when it comes to the application of digital twin and also its potential benefits. And there is also an increased interest in industry to utilize digital twins in these areas, in these stages. And of course, although manufacturing includes a wide range of different processes, we focus mainly on machining and assembly in manufacturing. So starting with the design stage, the concept of digital twins strongly exceeds, of course, established virtual simulation and product presentation models by providing a bidirectional and entangled connection for data sharing between the virtual and the real product, system or service. And this offers numerous opportunities to improve and optimize products and the corresponding manufacturing systems. In this context, digital twins basically widen the set of tools and techniques for design, and they connect digital representations of both product definitions and their manufacturing environments. And for product design and development, the added value of the digital twin is in this combination of various digital representations and establishing the link between products, product types, production tools, environments, and processes. We are able to render a coherent overview of the development cycles of products and production environments. Beside this, another added value of using digital twins in design is that all stakeholders, from client to developer and to operator, are supported with relevant, timely, tailored, purposeful, and adaptive information with the appropriate perspective at the right level of detail and aggregation. And this allows employees of the future to understand and also to interact with the entirety of available information in a meaningful manner. And moreover, of course, the digital solution that will be developed will present them with the design rationale of the development cycle, and it will facilitate decision making. Moreover, the digital twin and its data and information backbone allows for product, system, and service optimization with real-time feedback. Particularly in tolerancing and in geometrical variations management, which basically comprises all activities related to controlling geometrical part deviations and their effects on the product quality, digital twins have been identified as an enabler for exploiting fast efficiency potentials, for example, for real-time geometry assurance in individualized production, basically relying on the feeding of inspection data in advanced simulation models. Other examples for the use of digital twins can be found in the design and reconfiguration of smart products. And here, digital representations using computer-aided design and computer-aided manufacturing and service models are integrated, offering semi-automated reconfigurations of such smart products. Beside product design, of course, product manufacturing is a large and important application area of digital twins. And more particularly, of course, we all know that in machining, despite careful planning, all machining processes are characterized by variations such as tool wear or varying cutting conditions or material properties. And beside this, also axis interpolation and the actual dynamic behavior of the machine tool bring additional uncertainties into virtual machining processes. And consequently, there is often a difference between the product as planned and as machined. And in this context, the digital twin can help to consolidate data from process planning, machining, and quality control to improve manufacturing and to enable a self-optimization of the machining process. For that purpose, a digital representation of the workpiece is enriched with data from the process and quality control, like force measurements and geometry measurements. And a process parallel simulation allows connecting these measurements to locally resolved cutting conditions. And as a result, an accurate representation of the cutting conditions and the machined workpiece is possible without a control model of the machine tool. Next to machining, of course, digital twins offer fast potentials in assembly. For example, the application of digital twins opens up the possibility for individualized assembly of parts and thus also for increasing the geometrical quality of the assembled components and products. And in order to exploit and to use the potential of digital twins in assembly, of course, the acquisition and integration of real-time data from the entire production system is crucial. So feeding these data into the digital twin, the current system performance can be systematically analyzed and various options for improvement can be simulated, such as optimal production strategies by means of adaptive manufacturing and selective assembly, also in a function-oriented way. After design and manufacturing, products are typically used, and in the use phase, the maximization of equipment availability at a minimum cost is one of the key challenges in many industry branches, like for example in the aerospace industry. And in this context, maintenance, repair and overhaul operations have become crucial, especially for high-value products. Considering this, literature is increasingly paying attention to how a virtual system can adjust itself to the constantly changing conditions of the physical space of information that influences the operation dynamics of the maintenance, repair, and overhaul requirements. For example, health management looks at the remaining life of the asset and actually determines when the asset will fail. And also condition-based monitoring or maintenance are strongly relying on digital twin technology. However, the digital twin can also support the assembly and disassembly process and maintenance, repair, and overhaul. And it has been demonstrated how a digital twin can be used, for example, to overlay an existing physical product in order to locate specific assemblies and components and then bring up a series of menu options. It can also help to provide instructions on how to use the product, how to maintain it, and how to troubleshoot faults. And this is also, or can also be achieved with animations to aid instructions overlaid onto a physical product. However, we have to state that although some examples already exist in recent literature, the use of digital twins during a product's use phase is or can be considered still as in its infancy, and further research is needed in a number of areas. One area, for example, is related to the implementation of intelligent digital twins, which implies autonomous twins that do not require human input. And another area is the application of digital twins for multiple complex products, which refers to utilizing digital twins for multiple objects rather than a single object. So somehow a scalability of digital twins. So the last stage of our three-stage lifecycle model is the end of life and the recycling stage. And the end of life phase describes the final part of the life cycle when a part or a product can no longer be used as intended by the user. And in this stage, reuse and remanufacture and recycling operations are fundamental for a functional circular economy and are often used in a cascading structure. And in this context, we have to keep in mind that when we look at the critical decision of reusing or recycling a product or a part, this is most likely product dependent. So this is a key aspect for digital twin applications during the end of life. The item level access to information and data over the whole use history of the product. So this enables not only the better decision whether or not a part or a product can be reused or remanufactured, but it is also to identify alternate uses in another cascade level. And in this context, the digital twin can help to reduce warranty and liability issues in remanufacturing. And additionally, an added benefit of a sophisticated digital twin model is that it will provide access to the components, materials used, and bill of information as well. For effective and safe reuse of a certain system and their parts, having a seamless history of use and part origins via a digital twin may enable a better management of these equipment and the different end-of-life operations and strategies. So now that we reviewed some of the potential use cases of digital twins over the product lifecycle, the question is now, what are the new value stream patterns across the product lifecycle using digital twins? So as a short summary, we see here again the different use cases that we just discussed. So for example, in design, we have different applications and benefits of digital twins, like a virtual prototype, so a prediction of functionality, also an adaptive information carrier to stakeholders. This is something that I just discussed. Also the possibility for adaptive product design and also technical inheritance. In manufacturing, we saw that virtual machining, online and offline, and also the virtual quality control and prediction of functionality is enabled by a digital twin, which basically supports self-optimization and process planning, and it also allows some sophisticated assembly strategies like selective assembly. In the use stage, we saw that condition monitoring and health management is strongly supported by digital twin technology, and also maintenance, repair and overhaul processes are supported by the digital twin. And for recycling, we see that seamless product history and traceability of use is very important for the decision making in the end-of-life stage. Derived from this summary, we can state that during the beginning of life, the development of digital twins for assets, services, and products can be a novel business opportunity for engineering departments or specialized service providers, thus offering and selling adaptive information carriers. So the development of a digital twin for an existing product can be something that we can have new value stream patterns from. The use of digital twins in manufacturing offers also several opportunities for process optimization and new value streams. So while machine tool manufacturers already sell virtual machines for process simulation, new business models may arise from using the digital twin as soft sensors in manufacturing. And moreover, new value streams can, for example, arise from selling the operations or measurement data to enable product optimization based on accumulated data, using, for example, machine learning or artificial intelligence techniques. In usage and operation, digital twins foster the shift towards the operator model by allowing condition monitoring and health management, and thus a more accurate availability prediction of assets. And new non-ownership business models also depend on access to data and of the asset, and thus require a form of digital twin as their raison d'etre. Beside this, new value streams will emerge in recycling and remanufacturing, making use of the seamless product history stored and made available in digital twin information packages. However, in order to create these new value streams from using the digital twin, we also postulated in our paper some research challenges for design and production engineering, such as, for example, that the development and application of holistic digital twins, from our point of view, requires the work and expertise of many actors along the product lifecycle, and these different experts must move towards each other and work in interdisciplinary teams to fully exploit the potential of digital twins. So this is not only a research, but also some kind of organizational challenge. The connection and cross-linking of data and information from all stages of the product lifecycle requires also sophisticated data formats or data packages, which allow a coherent transfer of all kinds of information through standardized interfaces. So also standardization is very, very important in this context. A higher level of sensor integration is also necessary to monitor the product condition more closely and to update the digital twin continuously. And also, of course, in order to ensure fast computation, combinations of different simulation techniques as well as adaptive and scalable simulation methods must be further developed depending on the different applications of digital twins. What we also see that in most cases, optimization, for example, using digital twins, has been limited to separate stages of the product lifecycle. But in order to fully exploit the potentials of digital twins, these optimization procedures, which integrate different stages of the lifecycle and allow identifying global instead of local improvements, must be developed. So, summing up the presentation briefly, we all know that the concept of digital twins has received increasing attention recently, but actually we see that the current use cases in industry are quite rare. So based on a brief discussion of the different definitions of digital twin and also the emerging enabling technologies, we presented selected examples of digital twins and their usage in different stages of the product lifecycle. So this was actually the main part of our paper. And these presented use cases reveal that a broad range of applications based on digital twins can already be found in the literature, but the actual business cases are quite rare today. So motivated by this, we discussed some ideas for applications that might really create additional value streams at different stages of the product lifecycle, for example, in design or manufacturing, but also in the use phase and also in the end of life stage. But from our point of view, the boundaries between the stages of the lifecycle must be overcome in order to unleash the full potential of digital twins. And the derived research questions that we just saw on the last slide can be seen as a starting point for future research. So with this, I thank you also on behalf of all my co-authors for your attention and for attending the presentation. And I'm really looking forward to discussing your questions with you. Thank you.
Thank you, Benjamin Schleich. Thanks for doing the presentation, and thanks to all the co-authors. So this was a presentation of the paper, Shifting Value Stream Patterns Along the Product Lifecycle with Digital Twins. We are now trying to... Yes, we are now trying to get the connection to Benjamin Schleich. He's calling from Erlangen. Hey, Benjamin, very nice to have you here. Yeah, okay, so we can see you now on the stream.
So unfortunately, I cannot hear you.
Yes, try to use the Skype audio, please. Can you hear us now? Can you hear us now?
Audio issues.
Can you hear us now? Benjamin, can you hear us? Hello, can you hear us?
Now I can hear you.
Yeah, okay. Hi Benjamin, good to have you here in the session live. There was, in the stream, there were some discussions about applications and where does it make sense and in which way to approach the idea to implement digital twins. Can you tell us a bit more about what you have encountered about how to do the applicability, how to assess the applicability and how to find applications?
Well, I think the first thing that we did is that we made a survey among all the research affiliates from the different STCs. So we, in our research group or in the research affiliate group, we have 12 different research affiliates from different scientific technical communities. And we basically just had a look on the literature and the different applications of digital twins that are reported in the literature. So we found that there, just as I said on my last slide, there are already many applications of digital twins in literature, but the main problem for us is that there's also a question in industry when to apply it, and this basically depends on where is the added value of a digital twin. And when it comes to the added value, it's a little bit more difficult, and this is also what I mentioned in the last part of my presentation. So we already found out some possible applications with an added value, not only from a scientific point of view, but also where you can make money using digital twins. But I think we really have to exchange more with industry to find more different application areas where we already or also can make some money with digital twins and solve real industrial problems.
Okay.
But to give you a short answer to your question, I guess the main benefit lies in the operation of digital twins in the service and use phase. Okay,
so that takes me to the next question. You mentioned briefly about circular economy aspects or compatibility throughout the life cycle. Can you comment on these aspects regarding digital twins? How far is research going right now?
I think this is a question that I cannot answer in few minutes. So I guess research is establishing also in circular economy and also in applying digital twins in this domain. So I would suggest that everyone who's interested in this topic just read the paper and have a look at it. But I think at the moment we're just in starting of applying digital twins in different application areas, but of course also for issues like circular economy.
Thank you. There is one question which just comes from the YouTube live comment streams. It says, can you give a specific example of monetization of a digital twin?
Right now, I guess what we all know are the examples that we know from maintenance and condition-based monitoring, basically. So it's a service in the operation of large assets, and this is empowered by digital twins. So something like condition-based maintenance and health monitoring is only, you can only provide such a service if you have a digital twin and if you have a data connection between your physical asset and your digital model. And this is, I think, one large example, but as far as we found out, it's more or less the only one.
Okay, thank you. We have time for a short question I'd like to ask you. Can you comment on the paper writing process in this group of research affiliates?
So it was very, very efficient, I would say. because, well, as you know, the CIRP is a working academy, and also the research affiliates that everyone wanted to contribute something to the paper. So for us, for Mark and me, as the leading authors, it was quite easy to get some input from the different co-authors. And we had different meetings, web meetings. Of course, it also fits very well to the web conference, the CIRP web conference, this paper, because the paper writing process was also based on web technology. But of course, we also had physical meetings at the General Assemblies and the winter meetings of the CIRP. And this is a very, very good venue or possibility for young research to work together and to cooperate.
Benjamin Schleich, thank you very much for joining this session. Thanks for having the question answer. See you next time. Thank you.
See you. Bye. And thank you very much for the organization.
Thank you very much.
Thank you.
So this was the first presentation of the highlighted papers of the 7th CIRPe Global Web Conference. May I just highlight the hashtag that we ask you to use, or that we suggest that you use when you use LinkedIn, Facebook, Twitter, or whatever. Do commenting if you like. Give us feedback. Give feedbacks to the authors. It's really appreciable to see this live stream. I can see the live stream commenting here. It's really good to the activity that is going down there. We come into the second highlighted paper we have featured in this year's CIRPe Global Web Conference. As I said before, for those of you who might have joined a bit later, the highlighted papers are an idea to give space for collaborative work of research affiliates to develop a common perspective on a thoroughly discussed topic and there. The first one we have seen just right now. The second one that we are seeing now is entitled Highlights in Customer-Driven Operations Management Research. The leading author who we were contacted from is Khaled Medini, and he is teamed up with Anne-Louise Andersen, Thorsten Wüst, Björn Christensen, Stefan Wiesner, David Romero, Ang Liu, and Fei Tao. And I really appreciate that this is a true global collaboration. You can see by the list of affiliations below the title how many different time zones we have in there, how many different academic perspectives in here, and we are really pleased to see the paper presentation right now. Please.
Good morning. I am going to give this presentation on behalf of the co-authors of a highlighted paper titled Highlights in Customer-Driven Operations Management Research. The paper is authored by Khaled Medini from Mines Saint-Étienne, Anne-Louise Andersen from Aalborg University, Thorsten Wüst from West Virginia University, Bjorn Christensen from Aalborg University, Stefan Wiesner from BBI Institute at the University of Bremen, David Romero from Tecnológico de Monterrey, Ang Liu from University of New South Wales, and Fei Tao from Beihang University. The objective of this paper is to identify key challenges and opportunities in managing operations in complex customer-driven manufacturing, covering the value network, requirements engineering, product configuration, and the production systems, as well as the opportunities for handling these through digitally enabled methods and tools for materializing the Industry 4.0 vision of efficient lot size 1 productions. As you can see, the paper resulted from a large collaboration spanning over 4 continents and involving active researchers within different networks and communities, including CIRP. The basic principle for conducting this research is to build on each of the authors' backgrounds in order to get an overall vision of the research problem. This made it quite easy to structure the paper given the very complementary contributions from the authors, and which are all relevant to the main topic addressed by the paper. To start, let us have a look at what operations management referred to. Very briefly, operations management can be defined as the management of systems or processes that create goods and/or provide services. Operations management has evolved as well to keep up with the pace of the social and economic contextual changes. In fact, dynamic stakeholder requirements coming from both the customer but also from the solution environment are exerting more and more pressure on enterprises in both business-to-business and business-to-customer setups. This pressure is intensified by the tough competition, which goes beyond the traditional focus on price and even the time-cost-quality triangle, to span over a multitude of criteria. For instance, the mass production model focusing on increasing productivity and reducing costs is no longer prevailing, as it falls short on meeting the diversified customer demands while maintaining reasonable production costs. This traditional trade-off between high variety and low cost is met by the paradigm of mass customization, which focuses on integrating mass production principles with customization towards a customer-centric enterprise. These evolutions allow enterprises to cater not only large markets, but also long-tail markets where further value can be generated for both the customer and the supplier or provider. Several enterprises start diversifying their value offering and extending it with services, which however leads to an increase in internal complexity resulting from the external offering variety. We try here to investigate the opportunities towards customer-driven operations management considering the Industry 4.0 context. A typical example of customer-driven supply chain and even mass customization in practice is the Dell supply chain. A customer seeking a computer system with specific characteristics first goes online and places his order. At this point, the customer selects from the various options for the different aspects of the computer system. The personal computer system is defined in terms of specifications, for example memory size, processor speed, hard disk size, etc. Then, Dell produces a computer system as per the customer's needs. Dell can manufacture a built-to-order system of high quality and low cost and does this on a mass production scale to customers all over the world. Generally, the customized computer is delivered within 5 days. The ability to deliver such variety in such a short time is enabled by several complementary operational, tactical and strategic methods and tools. This Dell model and many other mass customization success stories are consistent with the vision of mass customization, that is to say the use of flexible processes and organizational structures to provide a variety of products and services that are designed to individual customer specifications, near the cost of a mass production system. Dell can manufacture a built-to-order system of high quality and low cost and does this on a mass production scale to customers all over the world. Let us move to the research method. An explorative research approach was adopted in order to collect preliminary information about the problem. The main sources of information are scientific articles and books published during the last decade. The authors analyzed a total of 53 publications referenced in this paper, including 28 journal papers and 10 conference papers. This analysis was guided by the collaborative manufacturing model, which offers a holistic vision into the whole value network. With its different views, the collaborative manufacturing model provides a partial but multifaceted perspective of operations management. The following areas have been identified in our analysis and will be addressed: value and value network, addressed by the value chain domain; requirements engineering, addressed by product and process design domain; product configuration, addressed by customer order fulfillment domain; and manufacturing system, addressed by plant or factory operation domain. For each of these domains, challenges towards customer-driven operations are analyzed and potentials related to the Industry 4.0 paradigm are investigated. Let us have a look at the first area, value network. The rapidly changing business context has shifted the focus of value from efficiency to a broader perspective involving other stakeholders beyond the company. In addition, competition and the increasingly challenging customer requirements compelled companies to seek more sustainable value. Sustainable value is thought out collaboratively by considering different perspectives, namely the market, the price for instance, the customer, for example customer satisfaction, and the traditional engineering perspective, function cost. Focusing on the value for multiple stakeholders implies a paradigm shift from managing physical products manufacturing operations to managing the operations of products and services. Ultimately, physical products can be used only as a means for delivering a service, and thus to create shared value. The main features of the value network within the Industry 4.0 environment are the decentralized structure of the value creation activities, and of the decision-making process, and the automation. Examples of horizontal integration enablers include intelligent transportation systems that are able to foresee changes and adapt accordingly due to the interchange of smart data in a decentralized way, for example, automated guided vehicles. Vertical integration relies on cyber-physical systems that are no other than smart systems with sensors, data processing capabilities and actuators for manipulation embedded in them for tracking and monitoring the value being created, and decentralized process optimization. The communication among the different cyber-physical systems is supported by the cloud paradigm. Customization and personalization lead naturally to a higher variety of products and services, hence presenting new challenges for marketing, manufacturing, warehousing, and logistics and distribution. Requirements engineering sets the interface between the designer, manufacturer, and the customer. The importance of requirements engineering cannot be overstated for the success of a development project. For the traditional paradigm of mass production, the large batch size operations can look back at years of experience, methods, tools and practices to support the process of soliciting, specifying, classifying, and validating requirements. However, within Industry 4.0, the system environment of stakeholders, technology and constraints is more dynamic, and changes have an impact on the requirements for the solution. This makes end-to-end engineering challenging, complex, as requirements will change over the solution life cycle. Today, not only the customer requirements are constantly changing, but also they are oftentimes inconsistent with each other. Furthermore, today's customers are increasingly motivated to share their personal experiences on the Internet. As a result, customer requirements tend to influence each other. Lastly, requirements should be formulated in consideration of not only customer satisfaction but also various aspects of manufacturing effectiveness. Main topics that need to be addressed for horizontal integration across the value network include involving users and other stakeholders from different domains actively in development from the beginning. To determine the unique requirements of a mass customized or personalized product or service, manufacturers need to directly connect, communicate and collaborate with small groups of target customers, if not individual customers, through involving users in the development from the beginning, adapting the solution to needs of the users, detailing requirements and mapping them to system elements, specifying formal requirements models, and integrating models. Configuration systems are among the most successfully applied artificial intelligence technologies in industries. Product configuration systems enable mass customization of products by allowing the user to combine product characteristics under a given set of constraints, which offers a vast range of product variants based on a global description of product design. Product configuration systems has over time developed from rule-based expert systems, like XCon, to mass customization toolkits enabling users to design and innovate products based on diverse requirements. However, current configurators and MC toolkits are still mainly based on expert system architectures. While knowledge can be acquired from experts and represented in the system's knowledge base, accessible through a user interface and inferred by an inference engine hosted locally. With increased customer-driven operations, current configuration systems face various challenges, particularly in terms of providing support for optimal configurations, particularly in highly volatile environments. For example, an alternative to acquiring knowledge from experts and representing it in a knowledge base, products can transmit operating conditions from the field and store them in a cloud solution. This type of data is referred to as big data since data volume is significant. Variety of data types such as landscape, documentation and performance output is large. Another example, reaching the preferred product during the configuration process is currently archived through inference from characteristic selection. This can be archived through simulations and optimizations acting on big data and machine learning. It is also further possible to transform the interaction with the product portfolio into augmented reality using the digital twin concept. Increased customer centricity forces factories and manufacturing systems to be highly flexible and agile and dynamically reconfigurable to meet customer-driven changes more efficiently. Being able to quickly adjust manufacturing systems to produce variants within part and product families. Adjust to new mass customized or even personalized offerings. As well as expanding systems to new product generations or market demands are main components of customer-driven manufacturing. Manufacturing systems must be co-developed jointly with product families and platforms and modules. They need to incorporate not only traditional functional requirements but also non-functional requirements of changeability and supportive enablers of reconfigurability such as modularity. Industry 4.0 related opportunities offer the possibility to increase changeability of manufacturing systems significantly, covering both higher horizontal and vertical integration to provide seamless integration and coordination of inside and beyond systems, and a higher extent of end-to-end engineering entailing system design for change and dynamic product requirements. Important features of reconfigurable manufacturing systems within the Industry 4.0 context include interoperability, to be easily integrated through standard interfaces to enable fast ramp-up and high-variety products. Transparency, referring to real-time information for example, like digital twins. Autonomy, suggesting that system modules are integrated autonomously to suit a product's processing requirements, for example autonomous failure detection, autonomous reconfiguration. However, the idea of reconfigurability appears to be requiring a paradigm shift in the industry, as dedicated rigid and static systems are traditionally designed and operated in manufacturing enterprises. The technological drivers of such a vision of smart, connected and autonomous reconfigurable systems are either present or advancing very quickly. However, the organizational, management-related and human barriers towards its realization are even more challenging. The presented paper contributes to new value stream patterns in the following way. The summary presented in the paper is intended to provide guidance to decision makers in particular, within SMEs, exploring the paths to customer-driven operations. Displaying the drivers as per the CMM model allows enlightening decision makers about new dimensions of the enterprise where the potential of Industry 4.0 comes into play. To unleash this potential, both the investment policy, integration issues, and value perception should be addressed. In fact, the decision to invest in more IT-based processes is hindered by a lot of uncertainty regarding technical difficulty because of lack of skills and return on investment. More specifically, The interdisciplinary nature and complexity of the solutions requires significant investment without a full estimation of the break-even point from the start. Therefore, a proper cost-benefit analysis is important to foster the tools and methods adoption, in particular within SMEs. In this sense, costing tools and methods should be fine-tuned to support a seamless evaluation process of the different options to pursue any initiative. Similarly, prior to engaging in any projects, it is important to carefully study and plan the interoperability of the various systems with versatile technologies. The interfacing should be well thought out to gain in connectivity and flexibility, and to move towards more customer-driven operations management. Successful application examples or lighthouse projects are a good way to analyze interoperability issues and establish benchmarks highlighting the potential of such an investment. This is quite consistent with findings from previous research highlighting the role of Industry 4.0 in a systemic performance improvement of the company. Also, looking at the drivers, it can be inferred that services continue to play a major role in customer-driven operations management. The implementation of Industry 4.0 tools can be seen as a catalyst and accelerator of this change. Now one could speak about delivering the value to the customer instead of delivering a product and/or a service. Variety and complexity management issues can then be addressed in a broader perspective across value network. Finally, in order to provide value to the customer along the complete life cycle, both the technological as well as the economic perspective have to be considered. The combination of Industry 4.0 technology with innovative business models has the potential to enable new and innovative value propositions. Their relationship can be seen as interdependent, or symbiotic. When looking from a technological perspective, the physical and ICT domains are complemented with services to deliver the solution. From a business perspective, Industry 4.0 enables smart services and new business models. Pursuing the trend of customer-driven operations management requires an adaptation of the practices and content of engineering education curricula toward more active learning approaches. These approaches are expected to increase the motivation, self-efficacy, and subsequent retention rate of the learners and train them for complex business environments. While the benefits of the variety are quite recognized, its induced complexity for the manufacturer or service provider may threaten companies' competitiveness with also a negative environmental impact. Modularity and product differentiation postponement are among the most common means to deal with complex product and service offerings while keeping a bottom-line variety to meet customer demands. However, companies need to deal also with the hidden costs and environmental impact of this increasing complexity, which may very well top the benefits of a large product and service variety. An appropriate way to deal with this risk is to pursue a customer-centric process for acting on the offering variety and on its induced complexity. Acting on the variety refers here to decisions regarding whether to keep some specific products and/or service items, with the follow-up question, in which quantities? Acting on complexity consists basically of applying methods such as modularity and postponement to increase the standardization, and thus leverage the economies of scale, within the operations. Consequently, efforts on increasing the sustainability of personalized products need to be twofold. First, environmental sustainability should be considered as a decision criterion for the company when complexity is a factor, and second, decisions involving variety need to consider both economic and environmental sustainability factors. Here are some project examples about the general topic of the paper and in each of which at least one of the authors is involved. SUSTAIN stands for Steering Variety and Complexity in Operations Management Towards Sustainability. Variety stands for Variety and Complexity Management in the Era of Industry 4.0. For further details, please get in touch with the authors. The presented paper sheds more light on the tools and practices supporting customer-driven operations management within the Industry 4.0 context. The results of the paper are likely to enlighten decision-makers during the early investigation steps prior to adopting any of Industry 4.0 tools. In a nutshell, Industry 4.0 provides a favorable climate for improving customer-driven operations management. This impact on operations management goes beyond being purely technology-based, but the human element remains crucial. While this work attempts to complement the literature by putting together customer-driven operations management and Industry 4.0, there are still open research issues, in particular, a full roadmap supporting companies and particularly SMEs. Finally, proactivity is required on the side of academicians so as to design adapted course content and use appropriate teaching methods to prepare up-to-date trained engineers. This slide shows only a few references. For the full list, please feel free to look at the paper and/or contact the corresponding author. Thank you for watching. In case you would like to get in touch with any of the authors, please feel free to email us. In the meanwhile, please feel free to read the full highlighted paper highlights in customer-driven operations management research.
Thank you, Khaled and colleagues, for putting together the paper Highlights in Customer-Driven Operations Management Research. We're now trying to get through to Khaled Medini, the leading author of the paper, to have questions answered. If you have more questions, feel free to post them in the comments. We will have 4 minutes for that discussion. Thank you. Khaled, hello, welcome to the session. Thanks for coming to us. We are calling to you to France. Can you hear us and see us?
Yes. Yes, now I can see you.
Okay, thanks for putting the paper together and thanks for doing the presentation. We will have 3-4 minutes for discussion right now. There was one question arising about the implementation of that. What you presented in the paper is, let's say, it's a framework. How will we see implementations of? How do we get closer to implementations? Please.
Thank you very much for everything, for organizing the whole, the connection and the conference. It's nice to be here. To answer the question, yes, actually what we tried to work on in this paper, and where we started, the first step is to provide an initial, let's say, guideline for helping like decision makers going in this path towards Industry 4.0. Like, this is the very first step before making the choice on the technology, on the method, to position themselves in this framework. Shall I, for example, focus, if I'm going to focus, for example, on the customer side, what kind of tools do I need to investigate or to start benchmarking prior to moving to the feasibility analysis and to thinking of the investment and so on. So this is the first, first step and first guideline to direct the choice of a decision maker.
Thank you. The second questions I like to ask you, can you comment on the paper writing process and how you worked together in order to put all the contents together for that paper?
Yeah, thank you. Yeah, actually, the writing process was quite amazing, a bit challenging. Of course, international collaboration. It's something very interesting, and at the same time, it requires some, let's say, well thought out process for putting together all the efforts. And so it was like this topic was broad enough in order to put together the contributions from all the authors within this paper, and it helped us to find and identify new perspectives for working together about this topic. So it's quite interesting, and I think it's just first step in the path to collaborating on this topic.
Okay, so we might see more of the discussions that are going on the next CIRPe meetings on the research affiliates then.
Yeah, I hope so too.
Okay, so thanks Khaled for being with us, for joining us for the paper question and answer. Thank you so far and for the paper.
Yeah, thank you very much. Thank you for everything and for the organization of these sessions. Yeah. Thank you.
So this was the second highlighted paper in the program, which ends the session of highlighted papers right now. We're now coming to the second part of the first day. You can see the program right here. We're going to start the paper session on this live stream, and in parallel the second live stream will start. So maybe you just open a second browser window to follow us to the second live stream. Pina Bilge is going to do the moderation over there. In this live stream, we're going to start with papers about development and testing of a combined machine and process health monitoring system, a web-based platform for data analyzing and monitoring, and towards a connected factory, shop floor data analytics in cyber-physical environments. These are the three upcoming papers here. Let's just briefly have a look at the second live stream. We have a look at the second live stream. This is, just a second, that's going to come up. It's going to start with a survey from the University of Stuttgart about cloud manufacturing platforms. They have done a very interesting survey of a number of resources that relate to the paradigm of cloud manufacturing. Next paper there is about artificial intelligence in scheduling and motion planning, and more robotics and automation papers are going to come up there. So feel free to go over there. It's the same technical means as we are doing here on the first live stream. Go there, do commenting, add questions to the authors. They also going to have question and answers with the authors there. We're going to start here with the next paper. For those of you who have joined later, this is the CIRPe Global Web Conference. This year we're sending live from Berlin. We're having paper sessions now, 20 minutes per paper, and we will have a question and answer session after each of the papers. This conference is organized each year by research affiliates. It's been since 2013. This year from Berlin and Kaiserslautern, and next year from KU Leuven in Belgium. So we're going to start our paper session with a paper which comes from Sheffield. The main author is Javier Dominguez Caballero, and the co-authors are John Stammers and James Moore. The paper is entitled Development and Testing of a Combined Machine and Process Health Monitoring System. The group in Sheffield, they're really renowned for their machining research, so I'm really looking forward to see this presentation.
Hi, I'm Javier Alejandro Dominguez Caballero, and this is James Moore, and in this presentation we're going to talk about our research on the development and testing of a combined machine and process health monitoring system. Throughout this presentation we're going to talk about the background of this research, the experimental setup and method that we used, the analysis techniques, the results we had, and the conclusions we found, and the future work or next steps of this work. Now, there's plenty of evidence in academic literature about the analysis of sensor signals in a way that you can find different issues in components, cutting tools, and machine tools. Now, by identifying these issues in process, we can first limit further damage to the component or the machine tool, as well as prevent any additional damage to other components that were manufactured with the same issue. Now, there are commercially available systems in the market, but most of them often rely on static limits and they monitor single signals in isolation. Therefore, the objective of this research was to investigate advanced signal processing techniques and analysis techniques for a machine and process health monitoring system that utilizes a consolidated suite of sensors and machine tool, mainly to gauge the quality of the machining operation whilst the component is being cut, as well as the machine tool's performance. Now, the monitoring system that we used consisted of 3 main sensor systems. The first one was a 3-axial accelerometer in the spindle of the machine. The second was another 3-axial accelerometer in the test bed. And finally, a power monitoring kit to get some power signal from the machine spindle. We acquired all the signal through National Instruments equipment, as well as controller data through MT-Connect. And the experimental work, the machining trials, were done on a 5-axis DMG Mori CNC machine, where we machined 9 blocks of titanium using carbide insets. To gauge the health of the machine tool, we designed 2 fingerprint routines. In the first one, isolated linear moves were done where the spindle was located in the home position, then moved to each extreme of travel of each axis, and then returned to home. And this was done at 8,000, 40,000, and 80,000 millimeters per minute. The other routine we designed was a simple spindle rotation, where the spindle would be located at home location and spin at 20, 4,500, 9,000, 13,500, and 80,000 RPMs. This video shows an example of the first fingerprint routine, which is the isolated linear axis moves. To ensure that the tests were all comparable, mainly for the baselines, we used a calibration tool, as you can see in the screen. For the machining operation or the machining trials, we did shoulder milling around the 9 titanium test vehicles using the parameters on the screen. This allowed 10 layers of material to be cut for each test vehicle. This video shows an example of this machining operation around the test pieces. The failure moves that we simulated on the machine tool included a heavy tool, an unbalanced tool, a cold run that was done first thing in the morning, a warm-up run which was done straight after the warm-up of the routine of the machine tool, and the feed rate adjusted failure mode, which was a marginal reduction of feed rate and spindle speed override. For the machining trials, we simulated surface cracks by drilling small bores into the test piece before machining. We misaligned the part so that we will rotate the test bed to those degrees on the screen. And we simulated a worn tool by using a tool that was previously used in another test vehicle. The fingerprint routines were repeated 16 times in the layout shown in the screen. And for the machining trials, we machined, as we mentioned before, 9 test vehicles as well in the layout shown in the screen.
So to simplify the analysis, we had to segment the signal data that we'd recorded. So for example, we've got the individual axis motions here. So this includes the X, Y, and Z motion repeated at the 3 different speeds. So what we had to do was we had to segment each of those motions out from the recording, so we ended up with 9 individual signals. And this is the example in the machining operations. We segmented each of the machining passes out, so we ended up with 4 different segments from each signal that had been recorded. We then conducted a number of different analysis techniques in a bit of an exploratory fashion. The first batch was time domain analysis, and we were looking at the kurtosis, the RMS, and the signal mean of each of the signals. We did frequency domain analysis, including fast Fourier transform, and from that we were able to identify the most dominant frequencies in each of those. And then we also conducted time frequency domain analysis, including spectral entropy, as well as continuous wavelet transform. So I'm just going to give a brief overview of the results. There were too many to go through in any detail. So first of all, the ketosis, we didn't have much luck. We couldn't find any correlation with the simulated defects or faults in either the machining or the fingerprint routines. RMS, we were actually able to identify a drop in the RMS values with the spindle speed override applied during spindle rotation fingerprint routines, but we weren't able to find anything in the machining trials. Similarly, for the signal mean, we found a drop in the RMS with the spindle speed override applied for the spindle rotation routine, but again, nothing for the machining trials. And for the frequency domain results, we were able to find changes in the dominant frequencies across all of the different failure modes. But again, nothing for the machining trials. So we moved on to the time frequency domain analysis. So firstly, the spectral entropy. You can see here there are two obvious drops that we identified in the spindle accelerometer signal. And this corresponded with the points at which the milling head passed over the bores, but we weren't able to find any differences for any of the misalignment runs or the worn tools. We then moved on to continuous wavelet transform, producing these scalograms that you can see in the bottom right. They're very useful for illustrating how the frequency components change throughout time. However, it is quite difficult to notice any subtle changes by eye. So here I'm going to change from one of the baseline runs across to one of the feed rate override runs. And you can see, although there is a change, it is quite minimal, so difficult to discern by eye.
As mentioned, it was difficult to see any differences in the scalograms from a baseline test to a defect mode. Therefore, we designed a comparative technique which consisted of taking a number of these scalograms and concatenate them into a single matrix of 3 dimensions. This matrix was then used to calculate an average of the signal and calculate the standard deviation. Then, we used one of the test signals, one of the failure modes, and subtracted the average from the baselines to get an output signal, which was then filtered using the standard deviation to get a resulting image. Here you can see an example of how we used a number of baselines, as I mentioned, to create an average, which was then subtracted from a test signal, in this case a baseline, to get the resulting signal. As you can imagine, being a baseline, we expected to see very little signal elements. If we then use failure mode, in this case a feed rate override, we can see in the resulting scaleogram the signal elements that are highlighted by this defect mode. Similarly, with the machining trials, as you can see, here a failure mode, the failure mode of surface cracks with the bores, you can see in the resulting image how these bores are quite clear.
So, in conclusion, we're able to design and test a monitoring system that combines both machine health and process health through fingerprint routines and machining trials. We found that the majority of single quantity, time and frequency domain features that we tested were unsuccessful. But we did find that time frequency domain analysis, in this case spectral entropy and continuous wavelet transform, showed much better correlations to the induced failure modes than we found with single quantity values. We also were able to design a comparative continuous wavelet transform analysis technique which was able to filter and highlight any signal elements that were related to the induced failure modes. So, our future work. The comparative technique showed very good potential, and we believe that this could be used as a feature extraction technique for further analysis. The scalograms that are produced by the CWT could be analysed by machine learning techniques, including deep learning and classical machine learning. We could also use classical machine learning on the single quantity value time domain features, which we believe may help improve detection capability. We have actually already conducted some testing on this future work, and we're planning on getting this published in the Journal of Engineering Manufacture special issue on machining science at some point next year. The further machining trials that we conducted, they had streamlined fingerprint routines, streamlined machining operations and simulated failure modes. And basically that allowed us to gain much higher repeats to allow for the training and testing of machine learning techniques. And this included CNN fault classification, using custom-made networks and also transfer learning of pre-trained networks, and also classical machine learning classification techniques, including k-nearest neighbor, naive Bayes and classification trees. And we've been able to show quite good success with all of these. So we just wanted to thank the Catapult, High Value Manufacturing Catapult, for funding this research, and also thank you all for listening. Please let us know if you have any questions. Thank you.
So thank you, Xavier, John, and James for sending this presentation, for sending this article. We are now going to get live question and answers with the authors in Sheffield. So, hello to Sheffield. Can you hear us?
Yeah, we can hear you.
Yeah, hello, Franz.
Thanks for joining us. Thanks for being live here on the stream in this session of the CIRPe Global Web Conference. Thanks for the presentation, and we will have 3 to 4 minutes to have a discussion with you. The first thing that I'd like to discuss with you is about machine learning. You were revealing a lot of potential about these different methods in different domains that you tried out on your experimental data. What do you think is it going towards? How difficult will that be to find more applications of that in this domain?
So I believe with the, in terms of like the single quantity values, the feature extraction, it's quite difficult to notice any particular trends, as we showed by examining those in isolation. However, with the work that we've conducted since this research, we've actually been able to show that by running it through machine learning techniques, we're able to improve the detectability of faults substantially. We think that's a really good way forward with single quantity values.
Okay, thank you. So that brings me to the next question I'd like to state. It is about the implementation. So right now it's in, let's say, it's in a research stage right now, and it's you need a lot of trained, skilled resources in order to get that running. Can you tell us something about the prospective usage in more industrial environments? How much effort will there be left? How easy would that be to use and to implement? Can you comment on that?
Yes, of course. Well, as we mentioned in part of the presentation, there are commercial systems that try to do a similar thing, but the problem with those is they do it in a very somewhat simplistic way. I think for this, there are many options that this can translate into an application in industrial environment. For instance, to look on a combination of techniques rather than just a single way of detecting errors. Maybe have a different machine learning algorithms working parallel or with other systems like we discussed there at the end with deep learning to do a detection and then classification, that sort of thing. So I think that's potentially the way of moving this to a more complex scenario like industry.
Okay. Thank you very much for answering these questions. Thank you very much for doing the presentation and the article. So we're going to end this paper slot right now. Thank you. Goodbye to Sheffield.
Thank you very much. Bye.
So this was the first paper of this paper session. It was entitled Development and Testing of a Combined Machine and Process Health Monitoring System by the team from Sheffield. So for those of you who have joined just recently, this is the live stream number 1 of the 7th CIRPe Global Web Conference. We are in the middle of the paper session for today, 20 minutes per paper. There is a second live stream where there's robotics and automation related papers, which you will find in the channel description of this YouTube channel. And we're happy to have you here. If you like, do commenting in this live stream. We will pick up your questions here from the camera control room and then discuss them with the authors. So please place your questions during the presentation so that we can compile them and discuss them with the authors. And if you comment on social media, feel free to use the hashtag CIRPe. I think it's a very important thing to do the dissemination also of your own work and presentation here. We will cut the videos in pieces afterwards and make them accessible for you, for your reference, for your own marketing, so that you can refer to this video at a later point of time. We're going to the program of the live stream number 2, which is the other live stream, and I just want to keep you briefly updated about what is happening there. The next paper that is going to be happening over there is entitled A Web-Based Platform for Data Analyzing and Monitoring. No, sorry. I got the wrong stream. Sorry, I got the wrong stream. This stream is going to feature the next presentation, which I'm really happy to see that on this conference. It's coming from Stuttgart, the team of Alexander Ferrell, and it is authored by Colin Reif, Stefan Oechsle, and Florian Eger, and it is entitled A Web-Based Platform for Data Analysis and Monitoring, and we're going to see the presentation now.
Hello and welcome to the presentation of our development web-based platform for data analysis and monitoring. My name is Colin Reif and I'm from the Institute for Control Engineering of Machine Tools and Manufacturing Units at the University of Stuttgart in Germany. In the course of globalization and the associated challenges in meeting strict market demands, resource saving and efficient production of high-quality parts is becoming indispensable for the manufacturing industry. In today's multi-stage production systems, complex processes are performed in connected stages. In the case that a part deviates from the expected dimensions or a process stage has incorrect fabrication parameters, for example due to tool wear, the manufactured semi-finished product also becomes faulty. These deviations will propagate and reinforce through the following process steps. Defective products are often only identified at the end of the line, which leads to cost and time-intensive rework or even scrap. In comparison to the conventional procedure, including additional rework measures or possibly scrap, the zero-defect approach supports a dynamic and flexible reaction to deviations and defects identified at an early stage of the process chain. The proactive and forward-oriented downstream compensation requires multiple information gathered by multi-sensor systems. In order to achieve zero-defect manufacturing in modern multi-stage production systems, the project FORCE-ADM, founded by the European Union, aims at a comprehensive process optimization from an overarching perspective. Therefore, the big amount of data gathered by the multiple sensor systems has to be processed and analyzed, especially regarding the identification of correlations to determine influencing parameters, the modeling of relationships to predict future states, the monitoring of machine status, or the determination of compensation strategies. To realize these goals, a tool is needed which contains the required functionalities and logic, and allows the realization of statistical analysis and calculations. First, I want to point out the motivation and requirements for the development of the platform for analyzing and monitoring sensor data. The second point is a short overview regarding the state of the art. Subsequently, the design and implementation of the platform are shown. Finally, I want to make a conclusion and give an outlook for future work and additional application scenarios. Motivation. The main challenge for doing statistical analysis is that machine operators or mechanical engineers, which are familiar with the existing problems, are not expert in the field of statistics. On the other hand, data scientists or software developers often have not a required knowledge about a process which should be analyzed. Consequently, a gap between the actual application scenario and the development of a software solution arises. Accordingly, the goal should be to create a modular platform for data analysis, which is easy to use for machine operators and engineers to apply complex algorithms to solve practical problems. Thus, knowledge can be shared between domain experts, enabling the combination of the single competences and avoiding silos of knowledge. State of the art. According to a survey from 2018 by Katie Nuggets, Python is currently the most popular programming language in the field of data science and has replaced R. In order to be able to analyze data using the languages Python or R, sound experience is required since the necessary logic for processing the data must be programmed. Often, many calculation processes have to be combined to achieve the desired results. In addition, the execution of analyzing processes requires advanced statistical knowledge to be able to apply the corresponding methods effectively. Therefore, specialists, which are a cost-intensive factor, are required to carry out the necessary programming steps. This creates a gap between the analyst and the actual end user who wants to use the knowledge gained from the analysis for the application. Consequently, there are already a multitude of frameworks and platforms which aim to make these statistical methods accessible to users without basic programming experience. Therefore, visual programming approaches and additional support functions such as question catalogs and wizards are used. According to Gartner, the leading tools in the field of data science are RapidMiner, IBM SPSS, and KNIME. But these tools have some limitations that hinder the transfer of knowledge across different corporate domains. Most of these applications are often desktop-based programs. This means that an exchange of data, sharing of results and knowledge are limited. Furthermore, the available functions can often only be adapted to a restricted extent or with increased effort. Additionally, the most platforms are not based on Python. This means that the extensibility is often extremely time-consuming since the corresponding functions, which are often available in Python, must be programmed from scratch and linked via provided interfaces. Due to the identified deficits, this project aims at the development of an application which targets the key requirements: accessibility, which means that a user can access the platform without the need of installing a desktop-based application. Second, usability, which means the platform provides a visual programming interface for the easy usage of complex statistical methods. Third, the community idea, which means already implemented algorithms and calculated results can be shared with other users of the platform. And last, the extensibility, which means the integrated logic can be easily adapted and extended using Python. Design. To overcome the mentioned limitations and achieve the introduced requirements, the platform is designed as a web-based application. The architecture of the platform is based on a client-server model. The backend, deployed on the server, provides all functionalities and services and is developed in Python Django. The user can then interact with the front end of the platform using a web browser, which represents the client. The front end, created with the framework Angular, is responsible for coordinating the graphical representation of the functionalities on the client side, as well as for reacting to user interactions. The front-end communicates with the back-end via a representational state transfer, short REST, application programming interface. Using the front-end, different data sources can be linked and uploaded on the platform. To provide a platform which is as flexible as possible, the required methods and algorithms for data analysis are structured in separated processing blocks. These blocks, the so-called stages, are independent of the respective data they are meant to process. The goal in structuring the components required for performing analytical procedures, here called pipelines, is to make these usable for different application purposes. A stage is the smallest unit of a data processing operation and defines an individual processing step. These processing steps can represent different tasks. For example, the task of a stage can be to load data from an Excel file and to make it available for further processing. The task of a subsequent stage, in turn, can be to calculate a correlation from this data or visualize it. All data used as inputs and outputs of the stages have the same structure and are implemented as a class. This data object contributes to the modularity of the stages and enables a uniform processing. This ensures that all stages, as well as the front end, can access the attributes of the data in the same way. A pipeline contains all the stages used in an analysis process, as well as the associated parameters, and thus specifies the results of the calculation created by the user. The processing sequence is determined by the mentioned connection of the stages with each other. Stages and pipelines can be published and made available to the community. This makes it possible to perform typical and repetitive analyzing processes without reassembling the necessary stages. In addition, predefined pipelines created by data scientists or experienced persons can be shared to all other users of the platform. This enables also untrained employees to use advanced and in principle complex data processing algorithms for their specific use cases without the need of programming. A task corresponds to the entirety of an analysis process and consists of the associated pipeline and additional information. The purpose of a task is to execute a complete pipeline and display defined results on the dashboard of the platform. In order to ensure a uniform structure of the stages, they are derived from a template called abstract stage. The abstract stage defines the input and output and the execution of the logic. The function of a stage is defined by a single Python script and is stored on the server. The two properties input and output represent the interfaces to the previous and the following stages and transfer the mentioned data objects, whereas init and execute represent abstract methods which are used for the initialization of the settings as well as for the actual execution of the included logic. The settings can be adjusted by the user on the front end. This can be, for example, the selection of a processing method if a stage includes different possibilities. Implementation. The user interface for creating a new pipeline is divided into three sections: a list of available stages on the left, a visual programming area in the middle, and a view for setting parameters of a selected stage on the right. After inserting the stages to the modeling area, the ports can be connected. Using the visualization stage, the data of the respective port can be directly displayed. The visualization stage provides multiple displaying modes depending on the number of input ports. As soon as all inputs of a stage are occupied with connections, the execution of the stage takes place automatically. In this example, we want to know the minimum and mean value of the dataset. For this, we add the both required stages and connect the ports. A checkbox allows the user to mark the calculation as a result, which will be displayed on the dashboard. To save a pipeline or a task, additional information, such as a description of whether this pipeline should be public, can be entered via a dialog window. When the pipeline is marked as public, every user of the platform can access and use the setup for his own purposes. The dashboard represents the entry page of the platform. Here, to create a task are displayed with the corresponding results. Tasks can be marked as favorite, directly edited, or shared with other users of the platform. All visualizations are interactive and can be modified. Here you can see also the cyclic execution of a task. In this case, the calculation is updated every second. This would, for example, enable a continuous monitoring. The modular structure of the platform allows users to add or modify their stages. Therefore, you can go to a list which represents the collection of your stages and the pipelines. This collection looks similar to the Community Hub. If you want to adapt a stage, you can open it and make your changes with the integrated code editor. Here you can see the earlier mentioned abstract class with the init and execute method. The develop dialogs support the configuration of your Python script. You can add, for example, new settings, which will be automatically integrated in the code. Using the code editor, you can access the already installed libraries like pandas, numpy, scikit-learn, and many more. To save the stage, the user can enter additional information about the stage. The additional information can be the category, the description, or whether the stage should be public or not. Conclusion and future work. This paper introduces a web-based platform developed in Python Django for the modular analysis of data received from multiple data sources. Due to the modular architecture, a broad range of application scenarios can be addressed. The modularity is achieved by encapsulating single calculations and algorithms in so-called stages. These stages can be combined in processing pipelines. Through the integration of a visual programming interface for modeling the analysis steps, a higher usability is achieved. The platform offers the possibility of a cyclic execution of the created pipelines and thus enables continuous monitoring of processes. The developed platform shows a possibility to combine the exploitation and analysis of data with a community idea. The possibility of sharing stages and predefined pipelines in combination with modularity enables to map expert knowledge and skills with relevant use cases from non-specialists. The possibility of extending and adapting methods using an online Python code editor enables a high growth potential. Nevertheless, there are possibilities for improvement and extension of the platform. On the one hand, the implementation of further stages, especially stages for the integration of machine learning algorithms, would be conceivable. Additionally, a mobile version of the platform could be developed to extend the use of the platform in an industrial environment, especially at field level. The user-friendliness can also be further increased, making it easier for non-technical users to get started and use the software. This can be done, for example, by a kind of setup wizard when creating new pipelines. If you are interested in further information or have any questions, please contact me. Thank you very much.
Thank you very much, Colin Rife, for the presentation, for doing the article and the video. This was the paper, web-based platform for data analysis and monitoring. We're now trying to get live with Colin Rife to discuss some questions with him.
Hello.
Colin Rife, hi. Welcome from Berlin to Stuttgart. Can you hear us?
Yes, I can hear you. Thank you.
Thank you for joining the session. Thank you for being with us and for sending the presentation. We received one question through the commenting section, which is a very specific one. The question from Grim Schmidt was, can you explain the most relevant difference from Node-RED?
Yes, to be honest, I haven't used Node-RED until now, but I had a short look, and what I can see in the very short research, Node-RED is based on JavaScript, and our application is based on Python. So I think, in my opinion, for us it's easier to use Python libraries, which are very common for data analysis, and probably it's more difficult to integrate Python logic inside Node-RED, but to be honest, I am not very convinced to Node-RED.
Okay, so you reckon that the effort to implement the data analysis things will be more straightforward with Python than with Node-RED for that? Okay.
I think so, yes.
Yeah. Okay. Thanks for the answer. Maybe there's another comment coming up during the question and answer session, so that we can maybe be more specific about that. Thanks for the comment in the commenting section there. This brings me to the second question I wanted to put for you. How does your system compare to other established systems? I have seen in the paper that you were mentioning more, let's say, desktop style, or let's say more or less graphical interfaces than the one you're putting. This brings some advantages, but will also surely bring some disadvantages. Can you comment about that?
Yes, of course. So our approach was to create a platform with a community idea. So we have the possibility to share all content with other users, which are also registered on the platform. This enables, for example, that untrained users can use pipelines and analyzing steps from persons which are very trained and know what to do. And so it's very easy to transfer knowledge between experts and non-experts, and also to enable non-experts to use complex analyzing steps in their application directly. And another advantage of the web-based approach is, of course, that everyone can access it independent of the device. You only need a web browser, and also for maintaining the platform, you don't have to install and update your local application on your desktop PC. We have only one server which has to be maintained and updated.
Thanks.
Of course, there are challenges. I think one of the main challenges, especially for industry, is that they have to upload their data to the platform or to the server, which is probably a problem for most of the companies. But this could be solved, for example, when we would install or host the server in the local company network.
Oh, that sounds very, very interesting. Can you tell us more about the context of the research that is behind this paper?
Of course. So the development was made in an EU project, and the main challenge was there that we have a lot of industrial partners which have no experience in programming and, of course, not in data science, but they have the real problems which they want to analyze. So our solution was to develop a tool which can be used by the industrial partners as well. And because of this, we made this platform, and inside the project, they are already using it. So they apply analyzing steps which are created by us for their real data and for their real problems, and try to identify, for example, correlations. But also they started to train machine learning models of their process lines, etc.
Okay, can you maybe, I know it's a project in progress, but is there already a success story that you can share with us?
Yeah, as I already told, we have some correlations identified, but this is more on the data science aspect than on the platform approach. But also I had a lot of stories already in some applications where this platform was very useful. For example, when a colleague from an Italian company asked me how he can identify a correlation between a temperature and a quality parameter in his production line, I could prepare the analyzing pipeline for him, and the only thing he had to do was to input his data in this already existing pipeline. So for him it was very easy to use complex analyzing steps.
Okay. Thank you very much for sharing these insights with us, Colin Reif. Thank you from Stuttgart.
Thank you.
Goodbye.
Bye.
So this was the paper, a web-based platform for data analysis and monitoring, prepared by the colleagues from Stuttgart. Before we proceed to the next paper on this stream, let me briefly announce the next paper that is going to be live on the second live stream that we have here live from Berlin. So the next paper, the third paper that we will have, will be entitled Model-Based Reconfiguration of Flexible Production Systems. So if you're interested in that paper, just open a second browser window and follow that stream over there. This stream is going to be going to carry on with the next papers that we have. So the next paper is towards a connected factory, shop floor data analytics in cyber-physical environments. And we will have after that more data-driven papers after that. So the paper that we are going to see now, it's submitted by colleagues from Hungary and Austria, David Giulia Bergman, Viola Galina, and Alexander Gal. And we are really looking forward to see the presentation of this paper.
Hello everyone, my name is David Gyulai and I work as a research fellow at the Research Institute for Computer Science and Control in Budapest, Hungary. My presentation is about a reference model for industrial analytics projects supporting the data collection, storage and processing tasks. The overall objective of this work is to support analytics projects efficiently and to provide real business value for user companies. The presented work is a result of a cooperation with Fraunhofer Austria, and all of the previous methods have industrial relevance as well as theoretical and research background. I think every one of you knows that we live in the age of industrial digitalization, and most of the companies are interested in IoT applications, cyber physical systems, and solutions that anyhow relates to Industry 4.0 or whatever we call it. Many of the companies invest significant resources and efforts in projects to increase their digital maturity and to obtain more effective and transparent production. In general, they are interested in getting insight, oversight, and foresight about the processes through analytics and optimization solutions. According to the surveys and our experience, most of the application cases relate to root cause analytics, anomaly detection, and predictive modeling. The success of these projects is typically measured by the return on investment associated with the project itself. Even in case a high quality and sufficient amount of data is available, preliminary statement of the outcomes is often impossible to make. It might happen that the available data cannot contribute to bring the expected results. This can lead to defensive corporate strategy, namely that the management hesitates or beware of starting an analytics project. This lack of confidence is mostly associated with uncertain return on investment, while it is important to highlight that the project efforts can be high, considering both the expertise and time factors. Here we aim at presenting possible ways to elevate low-level process data into higher level, enterprise level of the decision making. Recently, an increasing number of industrial analytics applications are integrated in IoT platforms. They enable to implement workflows and pipelines from the source of the data towards its utilization in the form of descriptive, predictive, or even prescriptive applications. IoT platforms are essential elements of connected factories as they provide the opportunity to collect data from multiple sources and to store and analyze them in a common system. They provide tools to manage a large amount of data in near real time and control the flow of the data from the source to its end use. There are several IoT platforms available for industrial deployment. Considering the industrial use, typical application cases include decision support for predictive maintenance, predictive quality control, inventory forecasting, and logistics analytics. However, there are only a few use cases that consider the direct application of the analytics models in production planning and control. Furthermore, data analysis and modeling are often done in the IoT platforms without a feedback linked to the enterprise IT, such as ERP or MES systems. The platforms are typically used for descriptive and predictive purposes, and they only support decisions indirectly. Our analytics approach aims at building pipelines through the enterprise IT levels from the production all the way up to the corporate management. The proposed reference architecture for industrial data analytics is illustrated here. It is built up of four main layers: the data collection layer, the data lake, data processing, and analytics layers. They are all interconnected, involving the ERP, scheduling, and MES systems, and they not only support the flow of the data upstreams but also downstreams. We believe the results achieved in the analytics layer should not be independent ones, but they need to feed back to the decision making, such as planning or scheduling. Different technologies support to implement the layers of the architecture. Here I highlighted only some of them that we used in our demonstration example. Of course, we know that the model is not universal and not an all-rounder, but is generic enough to adopt it to various use cases. We think this general representation is useful as we could apply it successfully in various industrial analytics projects, and we could support the partner companies to increase their overall effectiveness with various analytics solutions. Let's see the layers of the architecture one by one. The data collection layer implements the link between the physical and cyber parts of the system, applying processes and various assets can be collected even in almost real time. The data collection is done through various communication channels and network protocols that meet the industry standards. Recently, wireless communication is gaining more attention from the industry. Among others, the major requirements towards the wireless sensor communication protocols are compactness, scalability, robustness, and low energy consumption. Typical IoT communication and messaging protocols include VLAN, ZigBee, Bluetooth, MQTT, and so on. As a central repository, the data lake is responsible for storing all the data collected from various sources, applying a raw storage format. In contrast to the data warehouses, structured, semi-structured, and unstructured data formats can be all applied. They are stored in a poly-based structure, including relational databases and non-relational databases, and also files. The data processing layer implements the functions that are needed to catch the proper data from the lake in the desired format. Database queries and file parsing approaches are used, and in many cases, various filtering and preprocessing methods are needed to get real, useful information about the raw data. Such methods implement data cleansing, data transformation functions, and in many cases, aggregation functions are also applied to reduce the volume of the data. In order to utilize the collected and preprocessed data, analytics, simulation, machine learning, and visualization models are deployed on the data analytics layer. These models directly provide results for the end users to get insight in the shop floor processes. Furthermore, the analytics models should be linked with the enterprise IT systems. Therefore, decisions made by using ERP, MES, and APS systems can be driven by data analytics. In order to demonstrate how we can use the presented architecture, a demo production environment was set up in a simulation environment, providing several application cases. In our testbed factory, we have three main segments. First, raw materials are processed in a machinery job shop that consists of 29 machines from 3 different types. Then the prepared materials are bundled in batches and treated in an oven. After the oven, a cooling conveyor takes place and products are then transferred into a mid-process inventory. In the assembly segment, 4 flexible, manually operated assembly lines are found, where human operators are assembling the finished goods. From 6 different raw materials, 12 finished good types are produced. An MES system with many functionalities are simulated, such as order tracking, completion logging, and scrap logging. In the assembly zone, product tracking is implemented with an indoor positioning system that collects the spatial data of the products in real time. The accuracy of the positioning system is around 20 centimeters, and the data is collected with a 5-second sampling interval. In order to demonstrate the functionalities of the data collection and processing layers, the indoor positioning data analytics is selected as a use case. Here we have noisy position logs about the products circulating in the assembly segment. Even though the nominal accuracy of the system is 20 centimeters, there are high positioning errors in some cases. In order to calculate the assembly cycle times and lead times, we need to filter this noisy data and mine out the real positions of the products over time. For this, we use a two-step approach. First, the raw data is accessed from the NoSQL database, and the Savitsky-Golay filter is applied to smoothen the position time series of each product. Then, the sequence of visited zones or workstations need to be calculated to obtain the real routing of a given product. For that, we use a knowledge-based filtering approach that relies on theoretical routing and information of a given product. Taking the filter's spatial coordinates, we calculate the closest workstations with a centering approach to each log entry in the time series. Then, a probabilistic filtering is used to accept a movement from one workstation to another, taking into account the theoretical routing information with the sequence of workstations and the idealistic cycle times. As a result of this probabilistic filtering, we obtain the actual cycle time of the products with some rapid calculations. For the visualization, a reactive web-based environment was deployed with the data lake and analytics engines behind. This dashboard supports the reactive call of the analytics and processing scripts and enables quick and efficient data visualization, filtering, and transformation. According to our experience, such applications support root cause analytics, anomaly detection, and predictive modeling, but they are relatively simple to implement and easy to use. Furthermore, they enable data visualization in almost real time, including the visualization of data streams. We selected 2 application cases to illustrate how the low-level data can be used to achieve real business value with higher-level data-driven decision-making. First, an adaptive scheduling approach is presented, where manufacturing data is continuously collected from the shop floor, especially about the machining processes. Here we apply machine learning algorithms to predict the job completion times under changing conditions. Having proper prediction models attached to the process monitoring, we can estimate the job completion times and recalculate the production schedule in case deviation from the original schedule is identified. With the earliest possible rescheduling, we can save idle times and increase resource utilization system-wide. Deploying this adaptive scheduling approach in the manufacturing job shop, we could reuse the execution make span of the schedules with 10% in average compared to the case when rescheduling was done only after the late task completions. In the second use case, we focused on the data-driven production planning of the manually operated final assembly lines. Here the main problem is the variation of manual cycle times that lead to lateness in the schedule execution. In order to tackle this, we continuously collect indoor position data and calculate the actual manual cycle times. Then we feed this cycle times information into the simulation model of the assembly lines and perform a scenario analysis to predict the system behavior in various circumstances. In this way, we can project the actual status of the system into the future and analyze the real capacity requirements of certain scenarios. Applying regression functions as simulation metamodels, we can describe the capacity constraints properly and optimize the workload balance between the operators to increase their effectiveness. In the analyzed cases, we could increase the parts per operator ratio with 15%. In my presentation, you could get insight into the development and use of a reference architecture for industrial data analytics. The goal was to present such cases where low-level data was used in high-level decision-making and multi-perspective analysis was performed in a prescriptive way. All in all, the presented tools enable fast and efficient industrial data processing using pipelines from the shop floor level all the way up to the enterprise level in the hierarchy. I would like to thank for your kind attention and please contact me for further information if you have any question or remark. Thank you.
Thank you, David Giuliai, for doing the presentation, for submitting the paper. We are now trying to get him live on the question and answer session. David, hi, we can see you now live on the live stream. Hello, can you see us and hear us?
Yes, hi Franz.
Hi, so thank you for doing the presentation and the article. The first thing I wanted to ask you in the question and answer session is you are mainly using a data-driven approach in the article that you're presenting, and we were wondering how does that relate, or what benefits would you expect if you would introduce model-based techniques such as were discussed in the highlighted papers about the digital twins?
Yeah, thanks for the question. So if you remember the four layers of the architecture, on the top layer and also in the right hand side of the figure, there are some model-driven decision making or decision support tools like the scheduling tool itself and some simulation tools. So basically what we do is that after collecting and transforming the data, we try to, if possible, almost real-time update the data in these models, but usually it works like periodically updating or refreshing the data in the models. Like in the scheduling model, we try to update the remaining completion or remaining durations and also the estimated completion times, and we try to reschedule the production as efficiently as we can. So in that case, the scheduling model itself is a model which is data driven, but it's not. It's a model-based approach. So and also in the simulation models, we try to periodically update the simulation model parameters like cycle times or inventories, just to represent the actual state of the system and forecast the future state based on this.
Okay, so we will see more of that. The second question, and at the same time the last question I wanted to ask you, there is a question in the live stream that we have received in the meantime, and it refers to the examples that you are using. And when I was looking through the paper, I have seen that you're working in the project context of an EU project. So maybe can you give us examples or such success stories from the project context to which you have applied or in which you have developed the contents that you have shown in the paper?
Yeah, thanks. So the project context is it's a European project. It's a quite long one, 7 years long project together with Fraunhofer partners from Germany and also from Austria. And basically, it's not a research project, but it's a teaming project where the project is about establishing a center of excellence.
And basically all the approaches presented in the paper relate to the industrial projects. So within this collaboration, we are establishing a Center of Excellence in Hungary, and we are aiming at working on industrial projects, in innovation industrial projects. So, and also this somehow relates to the question in the live stream. So yeah, it seems that it has some real world origins, but as I mentioned in the beginning of the presentation, the paper was written according to the experience of many industrial projects, and because of some non-disclosure agreements, we couldn't provide the real use case, but we tried to come up with the reference factory or with the model which refers to many of the use cases. So it's a realistic use case, and also the simulation model is very realistic, but it's not a real one. But we try to illustrate many industrial problems in a single use case. So maybe that are answers to both questions, maybe.
Thank you very much for the insights that you've given us. Thanks for joining us. And all the best for your further research at your place. Thank you very much. Goodbye.
Thank you. Bye-bye.
So this was the paper presentation entitled Towards a Connected Factory, Shop Floor Data Analytics in Cyber-Physical Environments from David Giuliai and his colleagues. The next paper that we are going to have on this live stream is from Germany, from the colleagues from Aachen. It is led by the principal investigator Günther Schuh and his colleagues Erik Regentisch, Michael Riesener, Torben Ipers, Christian Tönnes, Merje Hendrike Young, and it is entitled Data Quality Program Management for Digital Shadows of Products. We are interested to see the presentation.
Thanks for joining the presentation on our research on data quality program management for digital shadows of products. My name is Torben Ipers. I'm from the Laboratory for Machine Tools and Production Engineering of the RWTH Aachen University, and this paper was a collaboration together with the Massachusetts Institute of Technology, MIT. Our research is motivated by two trends. On the one hand, we have an increasing data volume that companies have to deal with every day. There is, however, a novel information system concept called the digital shadow, which promises to be capable of dealing with these growing data volumes. On the other hand, we have the data at the foundation of the digital shadow, but this data is only useful when it is available in a certain quality. And we take these two trends, the growing data volume and the digital shadow on the one hand, and the data quality on the other hand, together, and from these two trends emerges our research question. How can the quality of the databases of the digital shadow of products be optimized? To answer this question, we use design science research methods to develop a methodology for the data quality program management. Before I begin, there's in particular one term here that needs to be defined precisely, which is, of course, the digital shadow of products. The best way to define it is to contrast it with another term in this area, the digital twin, which is presumably even the more common term used throughout literature. But there's an important difference between the two. The digital twin is often described as the comprehensive representation of physical objects. That means, as you can see in the quote on the slide, it describes objects from the microatomic level to the macrogeometrical level. And in contrast to that, the digital shadow of products is only the sufficiently precise representation of real-world objects. I would even go as far as saying that the digital twin is utopian, whereas the digital shadow is what can actually be achieved in reality. And then we say digital shadow of products because we refer here particularly to a virtual representation of physical products. The methodology for data quality program management, which we have developed, is divided first into two phases: the assessment phase on the left side and the improvement phase on the right side of the slide. The assessment phase means that we want to evaluate the available data quality and derive potential needs for action. The second phase, the improvement phase, aims to set up projects for data quality improvement that are then bundled in a project program. If you look at the assessment phase, you can see that it consists of 3 steps corresponding to 3 submodels that we have developed in the paper. In the first submodel, we look at the different applications of the digital shadow in the company. In the second submodel, we consider the evaluation of the importance of these use cases with regard to overall company goals, because our goal is to prioritize the use cases and hence the data that underlies these use cases. In other words, the first 2 submodels give us a first factor to prioritize the data by use case importance. But we have a second factor which comes in the third submodel. In this submodel, we look at the actual data quality deficiencies and we want to evaluate in which databases these deficiencies are particularly severe, giving us the second factor, the data quality gaps. The 2 factors combined allow us to evaluate whether we have need for action, namely in databases with highly relevant and relatively deficient data. Needs for action are then targeted by data quality improvement projects. To this end, now in the improvement phase, we have one submodel which considers the configuration of data quality improvement projects. And I will now explain the 4 submodels in detail. If we want to evaluate which data has particular importance to a company, we have to look at the way the data is used within the digital shadow. We do this by looking at the different use cases of the digital shadow. What you can see on the slide are some prototypical use cases of the digital shadow throughout the product lifecycle, which is here structured into the 4 phases: define, realize, use, and retire. It needs to be said that our paper focuses on common expectable use cases, particularly for companies that produce physical products. So for other companies, slight adaptations need to be made, but also for companies with physical products, our descriptions are only of prototypical natures and adaptations need to be made or additions need to be made. But what is even more important here than the use cases themselves is the infrastructure of the digital shadow. What you can see is that we have different data sources which are integrated by the digital shadow to deliver information to the different use cases, where each use case has its own unique information requirements and also information quality requirements. Now that we have described the use cases, we want to evaluate the importance of these use cases in an organizational context. To do this, in the paper we have developed the digital shadow benefit impact model, which you can see on this slide. The benefit impact model consists of 3 dimensions: the strategic dimension, the managerial dimension, and the transactional dimension. And the model allows to rate the beneficial impact of the digital shadow with regard to overall company goals. As you can see, each dimension is further broken down. For example, the strategic dimension consists of customer alignment and competitiveness, architectural efficiency enhancement, and business innovation. Although we have so many factors, what we need in the end is just a single weighting factor for each use case. To achieve this, we are using the analytical hierarchy process. Maybe you already know the analytical hierarchy process. It consists of a number of pairwise comparisons. And in our case, it's first a number of pairwise comparisons of the use cases with regard to the factors of the benefit model, and then a pairwise comparison of these factors with regard to defined company goals. Like this, the single factors can be aggregated to importance weightings of each use case. As you can see in the example on the lower right corner in red, we have here 3 exemplary use cases, and each of these use cases gets 1 importance rating, 1 weighting factor to determine its importance. With the use case importance rating, we have a first factor determine our needs for action. But as I've said, in our methodology, we use a second factor, which depends on the severity of the data quality deficiencies. In order to evaluate the severity, we have developed a data quality model in submodel 3. Our data quality model has been derived from the plethora of existing data quality models in literature, but it makes a precise differentiation between information quality and data quality. As you can see, we have 6 information quality dimensions which structure the model, and then we have a number of data quality features which are assigned to the information quality dimensions and which are measurable attributes of the data. For example, we have the information quality dimension reliability, and reliability is expressed by the data quality features correctness, preciseness, and level of detail. One very important aspect in the context of data quality is the fitness for use principle. The fitness for use principle states that data quality is only meaningful with regard to the required data quality of certain application cases. So we cannot just measure the data quality features themselves, but we have to relate these measurements to defined quality targets, to a required data quality. We do this in our methodology by defining not only one singular requirements, saying that, for example, 80% correctness is what we want to achieve, but we define an interval of acceptable data quality with a lower bound and an upper bound. When we have this interval, we can now measure the data quality features and locate it somewhere in the interval, and then translate this location into a 0 to 100% relative data quality gap. The benefit of this method is that regardless of the unit in which the data quality features are measured, for example, processing speed, which is measured in a time unit, whereas preciseness is measured in a percentile unit, but regardless of the unit, we always have a relative data quality gap between 0 and 100%, and this makes the data quality features comparable. So we now have our two factors. First, the factor for the data quality deficiency, and second, the factor for the use case importance and hence the importance of the underlying data. And we can use these two factors to prioritize our needs for action. What we get is then a matrix of the weighted needs for action. The matrix has two axes. On the one axis are the databases, and on the other axis are the data quality dimensions. And from the matrix, the databases and information quality dimensions with the most severe need for action are selected and targeted with specific data quality improvement projects. The selection of needs for action can follow, for example, the Pareto principle. To support the configuration of a single data quality project, we provide in our paper a morphological box, which provides design variables in the design fields project type, responsibilities, and project extent. With regard to the information system, the application context of the database, and organizational characteristics, the project can be configured by selecting suitable variable values from the morphological box. An example can be the first variable, which is the orientation, and which can be corrective or preventive. The choice of this variable highly depends on the type of data that we're looking at, where frequently changing data is potentially better addressed by preventive measures than corrective measures. The final step is then the implementation and execution of the data quality project, which is, however, beyond the scope of our research. In design science research, it's vital to evaluate the practical applicability of the developed methodology. This evaluation usually aims to ponder the so-called, it's a common term, pragmatic success, which comprises both the efficiency and the effectivity of the artifact application in praxis. To do this, we applied our methodology in an industry use case at a German wind turbine manufacturer. As a result of this, 4 use cases were defined that sourced their information through the digital shadow from 9 data sources. As a result of the analysis, we defined, with the help of our morphological box, 6 specific data quality projects. Some of them have already been implemented by now by the wind turbine company. Now, if we look at the efficiency and the effectivity of our methodology, we see first on the side of the efficiency that we have one downside regarding the problem dimensionality. As you can imagine, already this matrix of databases and information quality requirements grows quickly in its dimensionality, so many inputs are required for our methodology. Nonetheless, we received the feedback from the data quality experts of the company that our methodology is a comprehensible and structured approach to the problem. Now let's look at the effectivity. Regarding the effectivity, there was one really interesting insight, because the result from applying our methodology was pretty much congruent with the intuitive a priori data quality expert estimates. And this tells us that our methodology is able to produce quite reliable outcomes. Furthermore, the data quality experts confirmed the suitability of our methodology for assessing data quality on the one hand and then deriving a suitable data quality improvement program. Okay, with this, I've reached the end of my talk. Thank you so much for your kind attention. I'm looking forward to answer any of your questions in the Q&A session.
Thank you very much, Thorsten Ipers, for doing the presentation and sending the paper in here. Data Quality Program Management for Digital Shadows of Products. We're now connecting to Thorsten Ipers from Aachen. Hello, this is Franz Friedrich from Berlin, 7th CIRPe Global Web Conference. Can you hear us?
Yes, I can hear you.
Thanks for joining us and putting the effort in the paper and the presentation. While watching the presentation, the question arose about can you clarify a bit more your understanding of digital shadows and digital twins?
Sure. So I think the term digital shadow is quite a new term, and it's not so widespread throughout the literature compared to the digital twin. The digital shadow is also a term that is more common in the German literature at the moment, I would say. But as we've said in the presentation, we see an important difference there. If you look at many of the definitions of the digital twin, you can see that one important point many authors make is that it is a pretty comprehensive representation of a real object, a comprehensive virtual representation. There's, for example, this quote of the microatomic to the macrogeometric level, which really well describes this comprehensiveness. And compared to that, the digital shadow is, as I've said, mostly in the German literature, often defined as the sufficiently precise representation of a real object. So there is already a selection of only the data and information that is important for certain use cases. So if you have a number of use cases where you want to use this digital infrastructure, then you have a selection of data and information that are provided to these use cases.
Okay. Yeah. Thank you very much. That brings me to the second question. We have 3 more minutes to discuss. How does that very conceptual work that we have seen right now, how does that get to use in real life application? What are the steps to be taken for that to be applied in practice, and how does it? Do you see very beneficial cases for that, or what is the application like that is very successful at that?
Yeah, the practical application was really important to us while developing the methodology. We used design science research, which has the goal to develop applicable design artifacts. And therefore, this applicability was paid a lot of attention to in all of our submodels. That basically means that most of these submodels really have factors that can be measured or can be determined. And if you determine all these factors, you can go through the submodels from the beginning to the end and then derive actionable data quality improvement projects. And we've also applied our methodology in an industry use case that was at a German company, a manufacturer of wind turbines. And we saw there that using our methodology, we could indeed derive a number of data quality projects. And some of these projects have also been implemented by now by this company and already show first successes in improving data quality and making the digital shadow more usable.
Yeah, I reckon that to handle the complexity of all the data and all the interconnection is quite a challenge in such kind of applications. Is there any particular comment that you can make on that?
Yes, that is true. It's indeed quite a lot of input factors that are required. The way we implemented it at this company was using an Excel-based model. So all the inputs were made in Excel, but still it was a lot of effort to do it. But I think it's still a good support method for improving data quality efforts in a company, using these factors and making the efforts to get the results.
Okay. Thank you very much for being with us in this question and answer session for your paper. So all the best to the colleagues in Aachen, and see you soon, or comment on the next papers. Thank you very much and goodbye.
Thank you so much. Bye-bye.
Bye. So this was the presentation and question and answer session for the paper Data Quality Program Management for Digital Shadows of Products, prepared by the colleagues from Aachen and Thorsten Niepers, live in this question and answer sessions. I would like to remind you and invite you again to do live commenting. Comment below in the commenting section. Put questions forward for the authors. We're going to pick them up and discuss them with the authors. Also, do commenting if you wish on LinkedIn, Facebook, or any other social media, so that the conference is being found and so that we get your feedback. What could be prepared or what could it be improved for the next time? Let me briefly highlight the program on the live stream number 2. The live stream, which is running in parallel, moderated by Pina Bilge. There is the robotics, automation and configuration session going on, and they are going to have the next paper, which is about a method for collaborative knowledge acquisition and modeling, enabling the development of a knowledge-based configurator of robot-based automation solutions. As far as I remember, that's from the colleagues from Greece. This next paper that we are going to see here is the paper which is about machine learning in production. It's a survey paper from the colleagues in Erlangen, from Jörg Franke and his lab. The survey, the review paper style is reflected also in the number of authors that we have here. The main author is Andreas Meyer, and he has teamed up with Dominik Kiskald, Moritz Meiners, Benjamin Lutz, Franziska Schäfer, Reinhard Seidel, Andreas Seelmeier, Jonathan Fuchs, Maximilian Metzner, Andreas Blank, and the leader of the lab is my colleague Jörg Franke. The paper is entitled Machine Learning in Production, Potentials, Challenges, and Exemplary Applications. Thank you.
Hello everyone, my name is Andreas Meyer and I'm a scientific assistant at the Institute for Factory Automation and Production Systems of the University of Erlangen-Nuremberg. On behalf of my colleagues involved, I will now talk about a recent paper called Machine Learning in Production, Potentials, Challenges and Exemplary Applications. While recent trends like autonomous driving, natural language processing, service robotics or Industry 4.0 are mainly based on the tremendous progress made in the field of machine learning. The revolutionary aspect of Industry 4.0 is the possibility of interconnecting technical systems in real time, so the data obtained in this way can then be analyzed and evaluated using machine learning techniques, aiming for improvements in terms of quality, lead time, cost, or flexibility. However, as broad as the subject area of machine learning is, as diverse are the possible application scenarios in production. Especially for small and medium-sized companies, a systematic identification and implementation guideline for the adoption of economically viable machine learning use cases are still missing. In particular, there is still a lack of a structured overview of concrete industry-specific best practices that can be easily transferred to one's own production. Thus, this paper is dedicated to give a structured overview of exemplary machine learning use cases across different processes and subsectors of the manufacturing industry. Well, in this presentation, as well as the underlying paper, we will start with an overview of relevant notions, basic potentials and main challenges of machine learning. Then, exemplary applications of machine learning in production are given from a process and an industry sector perspective. The process point of view mainly covers the main manufacturing process groups of DIN 8580, such as primary, shaping, forming or cutting. In addition, handling operations according to VDI 2860 as well as selected cross-process approaches are covered. From an industry sector perspective, application scenarios from various subsectors such as the production of electronics, electric motors or medical devices are outlined, and finally, we conclude with an outlook on future research and recommendations for actions are given. Well, so what is machine learning actually? Machine learning is a branch of artificial intelligence giving computers the ability to learn without being explicitly programmed. So, in general, a distinction is made between supervised, unsupervised, and reinforcement learning. In supervised learning, the machine learning model is trained based on a data set consisting of pairs of inputs and outputs, so-called features and labels. So supervised learning aims to find patterns within the training data that can be used, for example, for predicting product quality based on production data. In unsupervised learning, the computer also learns from data, but without previously known output data. So instead, the algorithm learns, for example, what typical sensor data of a machine looks like in order to be able to detect future anomalies. And in reinforcement learning, finally, a so-called agent is ought to take actions in an environment so as to maximize some notion of reward. Depending on the learning type, numerous algorithms can be applied. For example, artificial neural networks, convolutional neural networks, support vector machines, or random forests. So, as powerful as machine learning is, as extensive are the possible applications in production. So when it comes to predictive maintenance, for example, machine learning algorithms can estimate the condition of machines or tools and predict the optimal time for maintenance or tool changes. In quality management, machine learning-based models can be used to monitor or even predict the quality of the product based on process data. Applying machine learning in process control is expected to result in a higher adaptability to changing conditions, stabilizing output quality and reducing reject rates. Especially in the field of robotics, machine learning-based object recognition and motion planning have recently resulted in major advances. Other exemplary fields of applications include the job shop, scheduling, fault diagnostics, and energy management. A comprehensive categorization, however, of machine learning application cases in production is not yet known, and neither the aim of this concise overview presentation. Similar to Industry 4.0 use cases, machine learning potentials can be derived from technological opportunities, also called opportunity push, or an existing need for optimization, also called problem pull. Methods like value stream mapping, Ishikawa diagrams, process capability analysis, or expert talks can also support the identification of relevant use cases. So, in the next step, the selected use cases need to be concretized and analyzed concerning their cost-benefit ratio. For machine learning projects, the data availability and quality strongly influences this analysis, as extra sensors, data storages, and processing capacities require additional investments. And based on this, the prioritization and choice of the most relevant use cases can be conducted, for example, via a portfolio matrix. For the project execution, the iterative crisp aim cycle with its 6 phases represents the most established method. In the business understanding phase, the problem and the goals of the project are analyzed, understood, and specified in a project plan. The second phase, the data understanding, addresses the analysis of available data to gain first insights concerning the machine learning goals. So, data availability and quality represent a crucial requirement for even being able to apply machine learning. However, especially the connectivity of all planes still represents a major challenge. The subsequent data preparation phase consists of cleaning, transforming, and formatting the available data. With up to 70%, the data preparation is usually the most time-consuming part of a machine learning project. In the modeling and evaluation phases, these algorithms are trained and evaluated. So when choosing an algorithm, its robustness, that is to say, its response to unexpected situations, as well as interpretability play a major role. In case of a successful implementation, the project is documented and finally deployed in the real-world environment. So, irrespective of the industry, production systems usually comprise a selection of manufacturing processes in accordance with DIN 8580 and handling operations as defined in VDI 2860. While the underlying paper provides a comprehensive overview of machine learning approaches at process and industry level from institutes worldwide, the presentation focuses on a selection of machine learning use cases, mainly stemming from our institute. So let's go to the first use case shown here. According to DIN 8580, cutting describes processes in which a form is altered by means of reducing material cohesion. In this context, machining seems to be the most important subgroup. Typical applications of machine learning applied to machining include predictive maintenance, tool condition monitoring, predictive quality assessment, and monitoring of abnormal process behavior such as rattle. Qiskite, for example, detect anomalies like chattering using unsupervised learning and the non-negative matrix factorization method for dimensionality reduction. In addition, they demonstrate the capability for estimating the operational state solely based on the structure-borne sound without a permanent interface to the machine's control. For this, a modular system architecture for a data-driven monitoring system following the requirements of Industry 4.0 is proposed, as shown in the figure here on the right-hand side. So the second use case shown here. In accordance with VDI 2860, handling is a part of material flow and principle defined as the realization, defined change, or temporary maintaining of a specified 3D arrangement of geometrical bodies in a reference coordinate system. So far, a lot of machine learning applications address the autonomous planning and optimization of trajectories for articulated robot arms, as well as sensor data processing, for example, for 6D pose estimation. So in this context, for example, Blank et al. Present a pipeline combining so-called convolutional neural networks and template matching methods for 6D pose estimation. Blank's approach is especially suited for textureless industrial components. So in doing so, the convolutional neural networks helps to significantly reduce false positive pose estimations through a prior segmentation. The third use case shown here lies in the electronics production. The electronics production, the surface mount technology is widely used and thus requires extremely high yields and stable processes. The SMD assembly generally comprises 3 processing steps: solar paste printing, component placement, and soldering. So after each of these steps, additional inspection systems can control the process stability and identify faulty modules. As can be seen on this figure, machine learning can be applied for diverse use cases along the process chain. For example, since standstill cleaning highly influences the quality of printed circuit boards, machine learning can be applied to determine the right cleaning cycle. In the subsequent optical inspection, for example, solder joint images could be classified by convolutional neural networks. So the fourth use case shown here lies in the electric motor production. The electric motor production is confronted with increasing requirements due to electric mobility. Thus, the acquisition and intelligent analysis of process data promises great potential for tomorrow's electric motor production. So far, most of the existing machine learning approaches in electric motor production refer to the contacting process. The contacting process is particularly relevant for so-called hairpin windings used in the latest traction drives generation. So after assembling and twisting, the numerous contact points must be welded, for example, using a laser. To ensure a high quality of the whole winding, each individual weld seam has to be monitored for defects or other indicators of poor quality. So using machine learning, it is possible to assess the weld quality just based on images of the weld seam. Based on these images, defects such as holes and spatters or weld beads can be identified automatically. In addition, the electrical quality of the weld can also be assessed from this. Our first proof of concept at the Institute already showed good results, while we are still working to further improve the system. So the last use case is the X-ray tube assembly. The X-ray tube assembly underlies high quality requirements as it plays a vital role in a large number of medical applications. Well, unfortunately, the component for radiation generation in the X-ray tube can only be tested to full extent when assembled. Therefore, errors detected in this final inspection can be caused by a combination of variances in different upstream processes. In order to analyze the cause-effect relation on product quality, it is thus not sufficient to consider individual parameters in isolation. Instead, quality-critical parameters have to be analyzed across processes. In this context, Selma et al. Present an approach for the efficient cross-process analysis of product quality based on the standardized procedure which maps the well-known CRISPR cycle to the RAMI 4.0 architecture. Well, as can be seen from the exemplary applications, machine learning holds great potential in production. The process perspective mainly covers the manufacturing processes such as cutting, handling operations, and cross-process approaches. On the industry level, exemplary machine learning use cases in the production of electronics, electric motors, and medical devices are outlined. Although the structured overview is anything but complete, it is already a good basis to identify own use cases from an opportunity push perspective. However, most of the approaches mentioned here are still subject of research and not yet ready for practical use or even widespread. So this is the reason why research on the application of machine learning must be further promoted and the necessary data be provided by industrial partners. As always, it is important to simply get started in order to avoid falling behind in the long run. Well, the listed reference can also be found in this paper. Thank you very much for listening.
Thank you very much to the colleagues in Erlangen for that presentation. We're now switching over to the live call with Andreas Meyer. We have a phone connection with him established, which we are trying to get live just right now. Hi to Erlangen from Berlin. Can you hear us?
We can hear you.
Okay, thank you. That goes clear and well. Thanks for the presentation. Thanks for handing in the article and doing like the intensive review work. As we know from the FABS colleagues, you're really experts in the electronics markets and electronics production, and we really appreciated the paper also in this topic. What I was interested in is the electronics sector has always been ahead of other industries in regard of data and production data and usage of production data. Now that you see these machine learning things in there, do you also think they are ahead of other industries, or how do you think this correlates with each other?
Well, I think the reason for being electronics production so advanced in comparison to other industry is that we have a very high degree of automation in electronics production. And always when you have something automated, you also have data to evaluate. So that is the reason why electronics production and especially semiconductor production is very ahead of that in using machine learning. For example, electric motor production, it's also a mechatronic product. That here you see that we still have some challenges because of the manual work we have here. So only industries like semiconductor or electronics productions have a lot of data you can already use. Other industries like electric motor production are very handling intensive, so that you are not really able to evaluate, to analyze some kind of big data.
Yeah, okay, thank you. So the applications of the machine learning that you have cited and reviewed in your paper, would you estimate that the ecosystem of these tools and applications, will it be more into the broad sense, or will it go into in-depth, or will it aggregate to one aggregated tool set, or how did you observe that? How heterogeneous is this world that you have been into?
Well, as I already said, at the moment we don't have like a fully automated production chain in a lot of industries. So one has to look at one or two manufacturing steps. And that is the reason why we don't have like a huge ecosystem right now. We just have to focus on single steps and to evaluate how one can really use artificial intelligence in that step. Because in a lot of steps, maybe artificial intelligence doesn't make sense. There are like more sophisticated methods of statistics you could apply, but no artificial intelligence. So it really depends on. And when you have a look at the application scenario of handling, here you see that there's a difference between using machine learning in robotics or using machine learning in analyzing some data from machining processes. So it really depends on the application case.
Okay, thanks. That was a very clear statement. Thank you. Thank you for joining us in that question and answer session. Thanks for putting all the effort in the paper, and all the best for your future work. See you then. Goodbye.
Goodbye.
So this was the paper, Machine Learning in Production, Potentials, Challenges and Exemplary Applications, made by the colleagues from Erlangen. So let me briefly have a look at the program of Livestream number 2. The next paper that we are going, that you can see over there, is about a simulation framework for virtual robot programming in reconfigurable production systems. So Livestream 2 is in the middle of the robotics and automation session right now, and there are 3 more papers to come there. This stream that you are attending right now here, we are going to proceed with a paper made by colleagues in Belgium, Clément Dutoit, Pierre Deombreux, Edouard Lorfèvre, and Lucas Eketer have submitted a paper that is entitled Statistical Process Control and Maintenance Policies for Continuous Production Systems Subjected to Different Failure Impact Models. And again, this paper is a review paper, and we are interested to see the results of this group of authors.
Hello everybody, I'm Clément Dutoit from the University of Mons in Belgium, and today I will present my paper called Statistical Process Control and Maintenance Policies for Continuous Production Systems Subjected to Different Failure Impact Models, Literature Review. So for the industrial context, the quality has become an important strategy for competitiveness for companies because the improvement of production quality decreases the unit cost because there is less scraps, and so the non-conformity percentage decrease. The consequence is by applying preventive method we can save a huge part of the production cost. We have also a double link between maintenance and quality because maintenance action improve the quality of the production, and also the quality control can act as alarm to trigger maintenance action. So this is the reason why we want to optimize both together. The main objective of this paper is to propose a methodology to optimize maintenance and control chart for a continuous production system, and so to find the optimal value for the maintenance period, the sampling parameters, and the control limit. And so we will create a model, and the first step is to perform a maintenance literature review to understand the models for modeling production system, and special attention will be devoted to the failure impact models. That's to say, the way a failure modifies the monitor indicator, and the final goal is to reproduce a faithful model for the real system and optimize it. So the first step in the literature review is to identify the quality indicator, which is the most important features for the customer and its measurement. And so in the literature review, we'll see that the quality indicator is often modeled by a normal law, and the distribution function is given in slide 4. And we have to know that the real mean, mu, and the real standard deviation are estimated for the normal conditions to obtain this law. For the failure simulation, the most frequently used reliability law is the Weibull law, which can represent various mechanical behavior, and we have 2 parameters, beta and eta, and the cumulative distribution function is given in slide 5. And to obtain the failure time, we will use a Monte Carlo simulation. For the failure impact model, we have to model the impact of the failure on the quality indicator, and so this relation between failure and quality indicator is very important for the optimization of the control and strategy, because the control chart, the optimal control chart, it will not be the same. And it's not very developed in the literature, and the question is, we have a production system that produces items characterized by a normal law, and then we have a failure, but what happened after the failure? How is the quality indicator changed? And so there are 3 different models conventionally used in the literature. The first one is explained in slide 7. So the first model is a displacement of the mean of the quality indicator. So we have a normal indicator until the failure time, and then the mean is changed to obtain a different quality indicator. The second model is a linear drift in the quality indicator, as explained in slide 8. and then we have displacement of the mean and a drift of the standard deviation explained in slide 9, and after the failure the change, the mean and the standard deviation are changed. New failure impact model can be created by any combination of modification in the mean or modification in the standard deviation. For example, we can use nonlinear drift such as parabolic, exponential, polynomial drift, and these drift can have a physical meaning related to a given phenomenon or not. And the chosen failure impact model will be the one that best suit the real system data. And for a given system, it's important to know how the quality indicator is impacted, because the efficiency of the control chart will be different. Stochastic processes, we have also the possibility to use these processes to optimize preventive maintenance, because they can model the degradation, and so they can be used to model the degradation of the quality of the production. And so we will use gamma processes for their monotonic evolution, which seems better for modeling a quality indicator. So the stochastic process that follows a stochastic gamma process is defined in slide 12 with two parameters, the shape parameter and the scale parameter, and this stochastic process is characterized by positive increment, which can be used to model degradation. And so an example is given in slide 13 with different evolution for gamma processes. For the quality control, we have 4 different charts used in the literature: the mean chart, run chart, the exponentially weighted moving average chart, the cumulative sum chart. And so for the Shua chart, we have the mean chart, for which the indicator is the average of the sample. The control limits are given by equation in slide 15, and we have also the run chart with a quality indicator, which is the range, that's to say the difference between the maximum value and the minimal value. And so for the control limit are obtained with tabulated coefficient for this run chart. The exponentially moving average is a chart that consider the previous measurement, and so the indicator is defined in slide 16. And so we have lambda, which is the coefficient, the weighting coefficients, which allows to give less or more importance to the previous measurements. And the control limits are also given with some tabulated coefficients. For the cumulative sum chart, it's a chart which takes into account all the sample collected, and so the quality indicator is given in slide 17, and we have different parameters in this chart. The particularity of this chart is that there is no control limit, and so the interpretation of an out of control is obtained using the slope of the plot. For this literature review, we have some limitations, and so the first one is that in conventional preventive models we don't integrate the quality control. So for the use model, we will integrate the quality control in the maintenance decision. Secondly, when we have a model that deals with preventive maintenance and statistical process, we rarely integrate the process variable that affect the production in terms of quality. And so in the proposed model, the failure impact model is known and allows to quantify the quality loss. In the literature review, when we have a description of failure impact model, they are usually used. So it's a mean jump, a mean drift, and so the integration of gamma processes is more realistic and allows to model various quality degradation for a given system. And in the literature review, we have seen that it doesn't it doesn't exist a model that by data analysis allowed to simulate the behavior of production system with both these together. So for the model, we have a production system, a continuous production system. So we have a production 7 days a week and 24 hours a day with a constant production rate growth. The reliability law is known, beta and eta are given, and also the cost of non-production. And this system in normal condition produces some product characterized by a normal law. Okay, and if everything is normal, after a time period 2, we have a preventive maintenance that takes a time T2. Yes, and during the production, in fact, we have also the quality control that allows to know if the system is in degraded state. In fact, when we have a failure, the system goes through a degraded state and produce more non-conforming items, and so the quality control is able to know if the system is in control and then the production goes on, or if the system is out of control. And when we have an out of control signal, we perform an inspection that allows to confirm or not the failure. If there is no failure, the production goes on. If there is a failure, we perform a quality maintenance which has a time T3. And for the inspection, we have a time T1 and different costs C1, CI, CQ for the inspection and the quality. So for the methodology, we have to define the system with all this data. We have to select a failure impact model, select a control chart and a maintenance selection, a maintenance period too. And so after that we can simulate the production and calculate all the costs to obtain the total cost. And so the best maintenance policy too is the maintenance period that minimizes the total cost, and so we can obtain it easily. After that we can change the control chart parameter or change the control chart, and we can obtain the best maintenance period and the best control chart for each failure impact model by minimizing the total cost. So a short example is given in slide 22, and so we define the problem with some data. I will not explain all of them, but we have the data for the system, the production system, for the reliability law, for different time due to maintenance, for example. And then we have the definition of the failure impact model with a mean drift, a mean displacement, and a standard deviation drift. And we will use different control charts, run chart, a WMA chart, a custom chart, etc. And so the first result are the hourly cost, the number of non-dissection, and number of false alarm for each situation. And we see in this table that for a mean displacement, the mean chart is well suited and allowed to minimize the cost, and we have no non-detection. For the mean drift, the best chart is the EYMA chart, and for the mean displacement and the standard deviation drift, the L chart is well suited. That's logical because this chart is a dispersion chart. For the conclusion, we have a literature review to identify the different techniques that exist for modeling production system, and we have a first model for optimization of maintenance and quality control for continuous production system. These quality control parameters are fixed, and the maintenance periods is optimized in the numerical example. It allows a possible comparison between the different charts, and we can detect all the problems. We have different parameters that are calculated: number of false alarm, number of non-detection of the failure, availability. In perspective, we can integrate new failure impact model in the numerical example. For example, gamma processes. We can optimize each parameter using genetic algorithm. Maybe integrate imperfect maintenance or opportunistic maintenance. Modify the non-quality cost in a constant cost, for example. So thank you for your attention, and please, if you have any questions, feel free to ask.
Thank you, Clément Dutoit, for doing the presentation of this review of statistical process control methods in here. We're now trying to get Clément Dutoit live here on the stream. Hello, so this is Franz Dietrich from TU Berlin, CIRPe Global Web Conference. Can you hear us?
Yes, I can hear you. Hello.
Yeah. Thanks for being with us, and thanks for taking the time for the question and answers.
Yes.
The paper that you have presented contains a lot of conceptual and mathematical framework, and the viewers might want to know more about what is the application context to which this method will be helpful. Can you tell us more about this?
In fact, this paper was written for in industrial context. We have, in fact, industrial partners, for example, in the automotive industry with continuous production system. And in fact, the idea was for partners to optimize their maintenance and their quality control on their production system. And so this first study was made for understanding the different method and methodology to model a production system, and so this was the idea of this paper.
Okay, so how much did you have to remove from that specific example in order to get a grip on the problem, to be able to simulate this? How close is that to the reality that you have found in place at that customer?
So, for the moment, it's just in the paper. It's just a model, a global model, with not really a direct link with the industrial application. But for the industrial application, we still have much work to do, because we have to collect some data concerning the failure history, for example, to obtain the reliability law of the system, and then we have to know the quality indicator and also the way the failure influenced the quality indicator. So there is still much work to do, and after that we can apply the model and the methodology to the industrial problem to optimize the maintenance and the quality control for this customer.
Okay. How hard would that be to transfer this to other industries? Other examples that you consider in your specific project?
Yes, we have this partner in the automotive industry, but we have also partners in the railway application, for example, for the optimization of the railway track. And I think we can apply this kind of method in this context, even if it's quite different, because it's not a continuous production system, it's the maintenance of railway tracks, but it's still possible.
You're using the expression of continuous production systems. What is so important for your method that the production system that you consider is a continuous production system? Hello, can you hear us? Hello? Okay, we can hear you again. So what is, how important...
Sorry, there is a poor quality of... Okay. I can't hear you. Can you repeat the question?
Yes, sure. How important is it for your method that the production system that you analyze is continuous?
Yes, it's a continuous production system.
No, but why is that so important to have a continuous production system for your method? Is it also applicable to discrete production systems, for example?
I don't hear the question.
Okay, so it seems we have technical problems. right now. The connection is lost somehow. Okay, we will need to end the session right now. I'm sorry for that, that we couldn't discuss the last question anymore. Thank you for joining the question and answer session. I hope you can hear me right now. Thanks for being with us, and goodbye. See you for the next time then. I hope you stay with us in the YouTube stream.
Sorry for the problem.
So, goodbye.
Thank you. Goodbye.
Thank you. So this was the paper about statistical process control and maintenance policies for continuous production systems subjected to different failure impact models by colleagues from Belgium. There are 2 more papers on both of the YouTube streams we are having here on the 7th CIRPe Global Web Conference. For those of you who might have joined later, we're broadcasting this conference live from 2 studios in Berlin. The papers will be available through Elsevier in a few days. Feel free to open both of the live streams, and we are really happy to accept your questions that we will forward to the authors for them to respond in our live question and answer sessions. So there are 2 more papers to come up in today's program. The live stream 2, the other live stream, there is next the paper about AI-based computer-aided engineering for automated product design, and afterwards towards a digital twin for thermal processes based on a control-centric approach. This stream will have the next paper about a conceptual framework, and afterwards there's a paper which is entitled about smart trucking and status of the digital transformation of the trucking industry and a bibliometric analysis, a very interesting paper in my view. We are now getting to the paper before, entitled a conceptual framework of a digital twin to evaluate the degradation status of complex engineering systems. It is written by our colleagues from Great Britain, from Cranfield, Exeter, and London. And the main author is David D'Amico, together with Jen Arcoinchu, Sri Adipali, Christopher Smith, Ed Kewell, Jim Simpson, and Stephen Penver. We are excited to see the video.
Hello, my name is Davide D'Amico, and today I'm going to talk about my work titled Conceptual Framework of a Digital Twin to Evaluate the Degradation Status of Complex Engineering Systems, that I've done together with my research group based at Cranfield University, Exeter University, and Babcock International. Assessment with the ability to predict the remaining useful life of the asset of interest. In scientific literature, as we can see from the graph, after the introduction in 2003 by Michael Greaves, the interest in digital twins grew fast. Initially, digital twins were adopted in the aerospace sector. Nowadays, the implementation of digital twin is increasing also in the industry sector. Most papers study digital twins for specific purposes, like monitoring specific conditions or planning and managing specific phases of the life cycle. The use of digital twins throughout the whole life cycle, instead, is still in its infancy. This is probably due to the huge amount of data that has to be managed and for the complexity of the integration of different models that have been created to work in a standalone mode. There are many degradation assessment tools existing today. They study a different kind of degradation that may occur in a product. A degradation model must be contained in a digital twin framework in order to estimate the remaining useful life of the system of interest. The integration of degradation assessment model in a digital twin has been already started. A few authors, indeed, implemented some aspect of the degradation evaluation in their work. However, this is a highly complicated task, but can bring a cost reduction throughout the life cycle and a more conscious decision-making process. Better monitoring of the health status bring about to predictive maintenance approach and, of course, to a better maintenance planning. We are in the context of complex engineering systems, or systems that last for a long time and need a plan for the maintenance. Also, for those systems, there is an increase in the employment of the modeling and simulation methods, and as a consequence, a growing amount of available data across the product life cycles. This led to the use of the digital twin paradigm, which can combine the two trends. Moreover, in these systems, the implementation of the degradation assessment tools will result in a more profound evaluation of the status. The proposed conceptual framework is shown in the slide. As we can see, we consider the digital twin as a group of modules connected. We have a central unit where every other module is connected to. Each module has its own block with its own software, which can be different from the other blocks. Then we have the interface in each block, which translates the data into the common language of the digital twin framework. Each module has also its own database, which can store the data that might be needed in future iterations. On the left side, we have the cloud module, which can store the learning algorithms that will feed the experience-based model. The latter, indeed, can be useful in the case of connection with other digital twins of similar assets. On the right side, the visualization module, in which different kinds of visualization tools can be used to show the output to the user, for example, browsers, virtual reality glasses, augmented reality glasses, or a combination of them. The conceptual framework is composed of three main layers: the data architecture, the models, and the integration, or better, interconnection across the modules. This is also the order in which the digital twin should be made. The way each module communicates with each other can be compared to the way the main data provider on the web shares the data with other websites, without allowing them entering into the provider's architecture. This occurs thanks to the application programming interfaces, APIs. Here, for example, we can see a simple query response that may occur in the digital twin. The query is a structured string which asks to the system for a specific information, while the response is a JSON message that contains all the data that the query module might need. The central unit has the main feature of dispersing messages. It can receive a request from the module and forward them to the interested modules, ensuring the correct flow of data and messages. Furthermore, the central unit is also able to understand how many modules should be connected to the digital twin and checking their status, which can be on, off, or disconnected. This to ensure the maximum flexibility to digital twin. An example
So, sorry, we have to interrupt the video for just a second. We are having a short glitch in our player just right here in Berlin. We are in the middle of the paper of a conceptual framework for a digital twin to evaluate the degradation status of complex engineering systems. So sorry for the colleagues in England that this happened. So the camera control is restarting the video player in order to get that one sorted out. So hang on for a second. We're going to be right back at the start and step into the video at maybe the same place that where it got out.
The physical attributes such as dimension, mass, inertia, center of gravity, etc. Another model can be the environmental model, which can provide to the system information about the surrounding area of the asset of interest. Most of the time, indeed, environmental condition is the only difference between two similar assets and can bring to a different set of issues. The learning model, as I said before, can lie into the cloud and can contain experience-based algorithms that enable the simulation of the what-if scenarios. And finally, for instance, the degradation model, which can use the geometry from the CAD model and the real-time status of the asset from sensor and 3D scanners to generate the desired output and provide useful information for the prediction of the remaining useful life. The desired output and provide useful information for the prediction of the remaining useful life. Concerning the degradation assessment module, we use the example of the automated tomography inspection as a non-destructive test, NDT. When a part comes for a service, the maintenance system performs the automated inspection using pulsed tomography. With the use of signal and image processing algorithms, thresholds are set up to identify critical areas showing degradation beyond acceptable levels. The degradation model for this feedback-based maintenance is dependent on the data from the inspection system, existing knowledge on the history of the inspected part, and on the remaining useful life algorithms that help predict and establish a time to failure with a confident band. We can simply integrate this model into the digital twin framework. We only have to split the part of the evaluation of the remaining useful life and put it into the cloud, where the learning algorithm. Moreover, data-driven approaches such as machine learning used in a fleet context rather than a single asset can help in a long-term production planning to reduce unpredicted downtime, thanks to a data log history contained in the fleet digital twin. Indeed, as I said before, if we consider the fleet instead of a single asset for this digital twin management, we can use the historical information from other digital twins of similar assets in the same fleet in order to use the experience in our asset of interest. In this way, the knowledge of my asset can be enhanced and, as a consequence, make improvements during the design phase. In conclusion, this work wants to provide the framework of an open architecture for a digital twin, which is what is currently missing in the scientific literature. We can find first examples of open architectures, such as Eclipse Ditto, which is an open source architecture, but it still has some limitations and compatibility problems. The digital twin can also be used to virtually test the asset in different environmental conditions, or to virtually perform maintenance, testing different parts. Moreover, it can also have the hardware in the loop feature, which allows us to test modules in a virtual environment. In this way, the digital twin becomes an essential tool that contributes for a more conscious decision-making process. Future work will focus on the application of this architecture to a real use case, benchmarking the different communication protocols and libraries to speed up and ensure the correct circulation of information across models. Compare the result of an integrated approach with the ones obtained by using all the models and simulators in a standalone way. The final objective is to reduce the effort needed for the models integration as well as the integration of different commercial and open tools. Thank you for your attention.
Thank you very much for the presentation of this paper. We're now trying to connect with David D'Amico in Cranfield. Hello to Cranfield, this is Francisco from Turbulin, CIRPe. Can you hear us?
Yes, can you hear me?
Yeah, thank you. Thanks for joining us. Thanks for putting the presentation and the paper together. It is an interesting thing to see from the concept kind of way. Can you explain a little bit more what you mean with complex engineering systems there? So can you give examples? Can you explain that a little bit more?
Yes. Complex engineering systems are those systems that require maintenance and maintenance planning because they last for a long time. For example, engines, turbines, planes, ships. So are those systems that maintenance.
Can you repeat this, please? There was a technical problem on the way.
Yes.
So like the last two
sentences. Complex engineering systems are those systems that last for a long time. So they require a maintenance plan.
Okay. Thank you very much. So as we understood, there is a world of methods apart, and your paper is trying to propose a framework that integrates these parts. I wonder about, there is a lot of effort that is needed to do this kind of integrated approach in there. In what sense is the reward of that kind of integration to be expected?
Yes. Basically, nowadays the approach is to problem with silos, with standalone approach model, and then we use the data from our model to do another model and so forth. The idea of this approach is to have everything in one framework, in one structure, and let the models communicate each other in the way that they can share the data they need real time, and we can have the information we need real time, and so we can help our system to predict some failure to avoid downtime of the machine.
Okay. Does that mean more complexity, or does that reduce the complexity?
This means a lot more complexity, but more.
That was not clearly transmitted to you. Can you repeat that, please?
Yeah, it means more complexity, but also more flexibility.
Okay. What would need to be done in order to evaluate whether that is worth doing?
We need to develop the framework. We need to establish the common language of the digital twin, because each module connected to the digital twin should speak the same language. Mm-hmm. So the main part is to build the interface that can allow the models to speak with the digital twin. So mm-hmm. I think the main part is to let the model speak the same language.
Okay, so we're keen to see your future research in order to get that up and running in Cranfield. So thank you very much for joining us in that question and answer session right here. David D'Amico, thank you very much. Goodbye.
Yeah, thank you so much. Bye.
So this was the paper presentation and the question and answer session of the paper, A Conceptual Framework of a Digital Twin to Evaluate the Degradation Status of Complex Engineering Systems by the colleagues from Cranfield, Exeter and London, David D'Amico, John L. Koyenchu, Sri Adipali, Christopher Smith, Ed Keedwell, Jim Simpson and Stephen Penver. Thank you very much. We're now approaching the final paper presentation for today. On the live stream number 2, we will have a short look at the program. There will be another paper that refers to digital twins. It is entitled Towards a Digital Twin for Thermal Processes, a Control-Centric Approach. We refer to that channel for you. Open it in a second window. If you just joined here, now see the channel description, the YouTube channel description, navigate over there, leave a comment in our channel, leave a comment in the second live stream, and make it interactive, please. We are going to pick your questions in the live question and answer session again. So this channel is going to show now the presentation of colleagues from the West Virginia University. So the title is Smart Trucking, a status of digital transformation of the trucking industry, a bibliometric analysis. The authors are Mackenzie Keepers and Thorsten Wüst. We are really happy to see that paper in here, which has a little bit of a different content compared to the papers before, but I think it's a really interesting thing to have here at the 7th CIRPe Global Web Conference. Thank you. We're going to watch the video now.
Hi, my name is Mackenzie Keepers. I'm a first-year PhD student at West Virginia University in the United States. Today I will be talking to you about smart trucking, the status of digital transformation of the trucking industry, a bibliometric analysis. The motivation for this research stems from a project with an industry partner developing new I4.0 fleet management platform for the trucking industry. I'll run you through a quick overview. First, I'll start off with an introduction to smart trucking and a bibliometric analysis. Then I'll explain how we conducted this analysis in the methodology and data section. Next, I will explain the results from the analysis. We will close up with our conclusions and an outlook on future research. Okay, on to the introduction, where I will provide you with some background on the problem at hand and also put the research we conducted into a broader context. While it is fairly common to hear and see implementations of smart manufacturing and Industry 4.0 within a manufacturing setting, the application of these initiatives is only beginning to touch the trucking industry. We specifically chose to focus on only the trucking industry, so that means the part of transportation and logistics that directly involves a truck or tractor trailer. Currently, the trucking industry is mainly utilizing paper-based operations, even though there are technologies that exist that could aid in their smart transformation. One of the biggest problems currently faced by trucking companies is the shortage of drivers, which can be partially related to high delivery volume, tight deadlines, and that the truckers often want to be home at the end of the day. This way, they are no longer spending days at a time on the road and away from their family. The future state of smart trucking will see a plethora of real-time data. Ideally, the future of trucking companies will reap the benefits of the real-time data and have much higher operating efficiency through lower fuel consumption costs and more optimized routes, ideally in real or near real time. As previously mentioned, we used a bibliometric analysis approach for this paper. We decided that we were interested in looking at the publications by year, authors by documents and citations, keywords, and research focus area clusters. The goal of this research was to identify areas in which the trucking industry is exploring technologies that point towards a software-defined process. On to methodology and data. Here we will discuss how we went about answering our research question of what is the status of Industry 4.0 technologies and data-driven analytics in the trucking industry. Okay, some more information about bibliometric analyses. A bibliometric analysis uses mathematical and statistical methods to quantify findings from literature as specified by the researchers. The findings from a bibliometric analysis are based on literature metadata and thus are often a generalized version of what may be discovered from a typical literature review. For this research, we use the bibliometric analysis tool, VOSviewer, which is the industry standard and is widely used for bibliometric studies across different scholarly fields. We used Web of Science as the main data source because it provided additional high-quality results than Scopus did, another well-known database. This helped ensure that we were addressing all relevant articles. We began with the incredibly broad topic of trucking, which returned 23,264 results, of which most were not related to our smart trucking focus. We then added the idea of real-time data to bring us closer to our desired topic. This resulted in 291 papers. We chose to refine our search to only include articles and proceedings papers from the last 10 years. This timeframe also corresponds conveniently with the emergence of the term Industry 4.0 in 2011. We then narrowed down the papers to only 45 papers by reading titles and abstracts and ensuring that they clearly addressed the smart trucking topic and had a clear relation to the transportation of goods via truck or tractor trailer. These remaining 45 papers were used throughout the entirety of the bibliometric analysis. For analysis and visualizations, we used Microsoft Excel, VOSviewer, and Web of Science analytics tools. We also subjectively grouped the 45 papers into categories to facilitate further conclusions. This clustering was based on information provided through the title, abstract, and in some cases, full paper. Now for the fun part, results and further discussions. First, we looked at the number of publications by year. From this, we can see an overall increase from 2010 through 2018. It's important to note that this data was pulled from the database in May of 2019, and at that time, only one paper had been published for 2019. We do not find this to be significant. We believe the overall increase in publications can be attributed to growth of smart principles in businesses and increased availability of smart technologies. Next, we examined the number of documents each author had published. The goal of this part of the analysis was to determine if there was a group or groups focused on this research field. It was determined that the authors with the most documents had only published 2 documents. These are shown here. This tells us that smart trucking has a lot of unexplored research opportunities, and we expect this topic to continue to grow in its significance in both academia and industry. VOS-Viewer is a bibliometric analysis tool that provides users with almost any type of bibliometric data they're looking for. We used VOS-Viewer specifically for looking at the author keywords. VOS-Viewer clusters the keywords based on the keyword's association strength to the other keywords. In general, the keywords that most highly associated with one another will be closer together. For our results, we see 5 total clusters, indicated by the 5 different colors here. We also see 3 clusters which are completely separated from one another. This tells us that this research area is lacking a connection between supply chains, networks, and information systems. These connections are absolutely vital in the shift towards smart trucking. In order to pull some additional insights, we decided to cluster the papers using our knowledge of the industry. We sorted the papers in 3 different groupings. By method, which was the research methodology used, either real data or theoretical, which included simulations methods. By mode, which talks about what type of trucking company, and by what the paper primarily discussed. The top research focus areas were trucking locations and positions, sensors within the truck, and route optimization. This was no surprise to us because these seem to be the basic aspects of running a profitable trucking company. We also found that neither research methodology, real data or theoretical, was more dominating among the papers included in our study. For transportation modes, the field was generally split between container and less than truckload operations. For further discussions, we found it very interesting that there were only 3 papers included in our analysis which focused on cold foods logistics. We expected there to be a large amount of papers focused in this area because it is a highly regulated portion of the trucking industry. Another key point is that there were no papers discussing parcel transportation. We think that parcel transportation did not show in our results because these problems are likely solved in-house by large companies like UPS, FedEx, and other postal services. These companies have the critical mass and motivation to optimize their operations and utilize proprietary solutions developed specifically for their needs and requirements. Now for some conclusions and future research. To sum up, few publications were found which directly related with smart trucking. We believe this is because we are still in the early stages of this smart transformation. We also discussed the lack of connection between supply chains, networks, and information systems in the keyword analysis. From the yearly distribution of papers, we saw that recent growth in this research field can be expected to continue. Lastly, the current main research focus areas include route optimization, vehicle positioning, and vehicle sensors. We believe that some future research opportunities for smart trucking include addressing the missing link between business and technological perspectives within the trucking industry. As the smart movement begins to grow within smart trucking and we begin to see increased data availability, research could focus more on fuel consumption reduction, new warehousing methods, routing, and how to fill the driver shortage, just to name a few opportunities. And finally, smart trucking is on the horizon. We believe that smart trucking still has quite a way to go, but the transition has definitely started.
Thank you very much to the colleagues West Virginia for having that paper, Smart Trucking, Status of Digital Transformation of the Trucking Industry, a bibliometric analysis in this conference, the 7th CIRPe Global Web Conference. We're now trying to get live here in the phone call the author, Mackenzie Keepers, here with us. Hello, can you hear us?
Hello.
Thank you very much for joining us. Thank you very much. It's very early in the morning now at your place. Thanks for joining us.
Yeah.
Can you tell a bit more, the viewers a bit more about the method that you have used and how the bibliometric analysis is different from literature reviews and for what different purposes that may serve?
Yeah, absolutely. Thank you for having me and thank you for the question. So a bibliometric analysis is used to get a more statistical view out of the literature. We don't take the time to read through the papers unless we absolutely have to, which is rare. We chose to do a bibliometric analysis here just to get a quick overview. And then typically after the bibliometric analysis, you would go through and do a literature review on the papers that you narrowed down to. It gives you the ability to put some numbers to the qualitative word aspect of literature.
Okay, thanks for sharing this insight, and thanks for putting that together in a paper over here. Now, the second question would be about the motivation to do this survey. It's very interesting to say, okay, we have these Industry 4.0 things going on in manufacturing, and we want to see what's going on in the trucking sector. So, can you tell us a bit more about the context in which you do this research?
Yeah, thanks again for the question. We chose to do this on smart trucking because we had a partnership that we were working with someone in industry over here, and they are working on an electronic logging device, and they just kind of wanted to know where we're going in the direction of smart trucking and cloud computing with data for trucking. And so we said, well, we don't know, let's find out. So we did our bibliometric analysis to be able to say, okay, there is some stuff going on with smart trucking, and it started, but it's not really where we thought it might be by now compared to where smart manufacturing is going.
Okay. Thank you very much. Thanks for sharing these insights additionally to the presentation that we have seen. Thanks for being available for that call from West Virginia. Mackenzie Keepers, goodbye.
Thank you, bye-bye.
Goodbye. So this was the presentation and the question and answer for the paper entitled Smart Trucking, Status of Digital Transformation of the Trucking Industry, a bibliometric analysis authored by Mackenzie Keepers and Thorsten Wüst, located at West Virginia University in the United States. So this brings me to the end of this research paper session, the end of day one. We have had the opening session today. We have had the highlighted paper sessions, highlighted papers today, and we have had a number of research papers today. Many of them were revolved around shop floor operations and maintenance. Related topics. We have heard many contents about digital twins, digital shadows, about data that is gathered out of production systems and shop floor things for maintenance, for operations, and we have heard also planning, which is during the operations for the maintenance plans and so on. The second live stream has covered papers from automation, planning, and configuration, and is also coming to an end today, just in parallel to this stream here. For the second day, we have a look at the schedule for the upcoming 2 days. So tomorrow we have prepared that in 3 different colors. The first section of papers tomorrow will be papers around form-based processes and around metrology. So that I'm going to quickly read out the papers. It's the first one. We're going to start at 10 to 12 Berlin time, so that the paper session will start exactly at 12 o'clock. So the first one is evaluation of a concept out of autoclave process for manufacturing carbon fiber reinforced polymer automotive parts. That's from the colleagues in Tokyo. Then enhancing fiber length measurements performed by X-ray computed tomography for improving the production quality of composite materials. Also a paper which is around composite materials. And then a third paper about the investigation of mold filling and fiber injection molding based on image processing. Then afterwards there is another forming tool which is variable in its geometry from the colleagues from KU Leuven, Belgium. The second part of this session is about cutting, spindles and grinding, and it's the first one is a multi-objective optimization of machining parameters to minimize surface roughness and power consumption using TOPSIS. The second paper is about computational and experimental investigation of cutting tool geometry in machining titanium 6 aluminium for vanadium. Then the third paper in this series is about quantitative assessment of machine tool condition through fractal analysis of volumetric error vector similarity measures. So that's that for that second group of papers tomorrow in the stream. The third one is about value streams and lifecycle engineering. We have grouped papers that have these things in common. Then we will have a series of papers. The first one is about cloud manufacturing. The second one is about maintenance. The third one is about the configuration of turnkey production systems. The fourth one is about key performance indicators in logistics. The fifth is about Industry 4.0 in small and medium enterprises, which is again also a review-oriented paper. And then the day will end with a multidimensional assessment of value stream design alternatives. On stream 2, we are going to have two different types of papers, two different styles of papers. We are having research papers about robotics, automation and assembly, starting out with a paper from TU Braunschweig about incremental manufacturing, and then that goes on to through the day to the second series of papers about additive processes, coating processes, hybrid manufacturing and incremental manufacturing on day 2. We're going to have a look at day 3 as well. Just a quick glance. It's a very short program, but not less interesting. We're starting 1 hour earlier in favor for those time zones at the Eastern time zones at 10 to 11 Berlin time. Please be aware of that. Then we are going to have 3 research papers, and we are going to feature that very special industry panel discussion from 12 o'clock to 1 o'clock Berlin time, and then have a brief closing session on this live channel here. Then on this on Livestream 2, we are going to have 3 research papers which are about value streams and lifecycle engineering. So that is what we're going to see there, and then we're going to close that stream in favor of live stream number 1, where we're going to have the industry panel discussion at 12 o'clock noon Berlin time. In the meantime, we'd really like to see your feedback somewhere on social media. Don't stop commenting here on our YouTube channel. We really like to see you to use the hashtag CIRPe and then have some sharing of results and thoughts about this conference that we put together for you. This is the 7th CIRPe Global Web Conference, the end of the day 1. This is chaired by Nicole Krenkel from University of Kaiserslautern and myself, Franz Dietrich from TU Berlin. The conference is sponsored by the International Academy of Production Engineering. The conference is organized by the Research Affiliates, which is an organization within the world of CIRPe for younger researchers. It is the 7th edition of this conference. In the conference theme, we hope you enjoyed the first day of that conference theme towards shifted production value stream patterns through inference of data, models and technology. I'd like to thank people who have made it possible to put that together. It's the scientific technical committees, it's the reviews that have been submitted regarding the papers that we had today. It's the CIRPe sponsors, and it's at the forefront the authors that have been available for the question and answers today, the effort of the authors who have put together the articles and the presentations. Thank you to all of you. It's been a pleasure to do the moderation. Thanks for the time where everything went smooth from a technical point of view, and please accept our apologies for the short glitches that we had from time to time in our stream that we cannot have. So the last thing that I wanted to say for today, thanks to the team behind the camera. Thank you. In my case, it's Arne, who was Arne Glode, who was the camera setup guy, and Alexandra Weber, who did the co-moderation. And we hope to see you tomorrow at 10 minutes before 12 o'clock noon Berlin time again on this stream. Have a good day, have a good evening, have a good night. You all, wherever, in which time zone, wherever you are, we hope to see you again tomorrow, then in the morning, in the afternoon, or in the evening. Thank you and goodbye.